Good morning, everyone. I, Nisha, Assistant Professor in the Department of Physics, welcomes you all on the behalf of GGDSD College, Chandigarh, as we gather here today on the momentous occasion of National Seminar, that is Recent Advancement in Physics, RAP 2023. It's a privilege and honor to welcome General Secretary Dr. Anirudh Joshi, Principal Dr. Ajay Sharma, Registrar Ma'am Dr. Madhu Sharma, Chief Guest Dr. Navdeep Goyal, Retired Staff Physics Department Mr. Surinder Singh, faculty members from various departments, research scholars, my colleagues, and dear students to this intellectual conclave that promises a platform of exchange of ideas, knowledge, and inspiration. Special welcome to Chief Guest Dr. Navdeep Goyal, Dean Sciences, Punjab University, Chandigarh. Today, the college is hosting not just a seminar and is also fostering an environment of learning, collaboration, and growth. Our college has always been committed to nurturing young minds and facilitating the dissemination of knowledge, and this seminar stands a testament to the commitment. We are delighted to see the diverse audience present here, representing various fields, backgrounds, and perspectives. It is the diversity that enriches the discourse and adds depth to our deliberations. Our esteemed faculty who are experts in their respective domains, will undoubtedly enlighten us with insights and experiences. Before we proceed to our seminar, it's an honor to have with us the guiding force behind our institution, Principal Dr. Ajay Sharma, to join us and extend warm welcome to our esteemed guests and share their valuable insights with the faculty members on this significant occasion of National Seminar.
Respected Dr. Anirudh Joshi, General Secretary, GGST College Society. Respected Dr. Navdeep Goyal ji, Dean Sciences, Punjab University. Learned colleagues from different colleges and SD College, and dear students. Firstly, I congratulate PG Department of Physics for organizing this third national seminar on recent advances in physics. I know over a period of time, students and faculty members are waiting for this event because they are in a position to update their knowledge regarding what is happening uh, in the field of physics and allied areas. And I'm especially thankful to the Department of Science and Technology, Renewable Energy Chandigarh Administration for supporting this event, and also the DBT New Delhi for partially funding this program. Uh, Hopefully, you will be in a position to not only brush up your knowledge and skills, you will be getting a lot of information about the recent research. As we are having research centers also, and few research scholars are also present in the audience. I feel it is not sufficient to remain limited to the college. It's very important to go beyond the boundaries of the college to the universities and beyond, to understand what is happening and how it's happening. Only then you will be in a position to have the better knowledge, skills, and publication also. So I once again thanks all the present here for sparing the valuable time, especially Dikkoji. He was very busy, I know, these days because of certain elections also, and otherwise also he's working very hard for implementation of national education policy. But in spite of his all busy schedule, he has spared time for all of us. Thanks a lot.
Thank you so much, sir. I kindly request Registrar Ma'am Dr. Madhu Sharma to inspire and motivate the students with her words on the occasion of National Seminar.
Good morning, everyone. I think Dr. Ajay has already given a piece of advice to all of you as research scholars and participants that such events are meant for a discourse, an academic discourse which never goes out of date. However updated we might be within our own cocoon, sitting and deliberating on certain aspects of our subjects. But whenever there is an interactive session like conferences and seminars, they have their own importance. This kind of interaction, academic interaction, where people from various areas join in and the scholars, they have their inputs to give, becomes paramount for all kinds of research and the further trends to be identified for research work. Well, such occasions are to be applauded all the time, and it's so nice to see physics department come up with such a large participation in this seminar. Yesterday we came to know that there are more than 100 papers being presented, which is a large number, and definitely that shows, that speaks for the kind of work which is going on in this field. Physics has never been out of date, and it will. I would request Professor Joshi to bear it out with me on, even if we talk about metaphysics, even if we talk about spirituality, even if we talk about philosophy, even if we talk about any other area of science, physics go beyond it. So this is how we have to proceed in our endeavors for future trends as well. I wish you all the best, and I hope and wish that this entire exercise of holding this seminar turns out to be very fruitful by your interaction and coming up with new ideas. Thank you very much.
Thank you so much, ma'am. Now I request Head of Department Physics, Dr. Neelu Mahajan, to join us and represent the department.
Good morning to all. It is a matter of great pleasure that the Bosones Club Postgraduate Department of Physics, Goswami Ganesh Datta, Sanatan Dharma College is organizing third national seminar on recent advances in physics, RAP 2023. I would like to welcome my to Professor Anirudh Joshi, General Secretary, GGDST Society, worthy Principal Sir, Dr. Ajay Sharma, esteemed Registrar Ma'am, Dr. Madhu Sharma, and Professor Navdeep Goyal, Deen Sciences, Punjab University, Chandigarh. I would also extend a warm welcome to all the eminent speakers and my faculty members and colleagues and my dear students. I would like to take this opportunity to provide you the brief synopsis of our department. The Department of Physics was incepted in the year 1979 and it has become a long way to establish itself as one of the preferred choices of the students and has been continuously supported under the DPT Star College scheme, New Delhi. The department was conferred with the status of Research Center of Punjab University in 2017, and our department has 11 faculty members and 2 sports staff members. Presently, we have 6 research scholars who are pursuing their doctoral work with the department. The department has established high standards in teaching and learning for both basic and applied physics. On the behalf of the organizing committee, I would welcome each one of you to one day national seminar. Thank you all.
Thank you, ma'am. Now, a very special welcome to our chief guest, Dr. Navdeep Goyal, Dean Sciences, Punjab University, Chandigarh. Dr. Navdeep Goyal, Professor in Department of Physics, is a renowned personality. His main area of research focuses on experimental solid-state physics, dielectric properties of chalcocyanide glasses, device application of high-temperature superconductors, magnetic properties of layered semiconductors, and power electronics. He has more than 160 research publications. He was postdoctoral fellow TIFR Mumbai in the year 1992 to 1993 and in University of South Wales from 1994 to 1995. He joined as lecturer in Punjab University in the year 1995. He also has worked as reader in Punjab University, Chandigarh from 2004 to 2007 and has been working as a professor in Punjab University 2010 onwards. Sir, we are grateful to have you here. I would request sir to please come on stage and share your wisdom and insightful thoughts with us.
Professor Anirudh Joshi, Dr. Ajay Sharma, Dr. Madhu Sharma, colleagues, and students. We started the day with green welcome, and then I learned that the seminar is being sponsored by Renewable Energy, and that is something that I am going to talk about today. Topic that I have given for this keynote address is transportation, pollution, and green energy. See, when we talk about air pollution, because that is something which is actually a problem these days, particularly for populated cities. And major sources of air pollution, as we know, can be burning of fossil fuels, industrial emissions, indoor air pollution, wildfires, microbial decaying process that we see in our houses, transportation, then burning of garbage, construction, demolition. All these things are actually responsible for air pollution. But when we talk about transportation, it's a major pollutant. See, while about 10% people travel by air worldwide, but around 70% people actually use cars. They don't use even public transport. And so that is the reason that pollution by cars is maximum, and that is so particularly in urban areas. Now, the problem is that when we talk about pollution, pollution affects our health. And interestingly, if we try to spend 1 rupee or $1 for reducing air pollution, that will actually save $9 in health services. So that is the reason that world over everybody is trying to look for the solutions to air pollution. That is something that is happening, and that is the reason that people are looking for new ways of transportation. Right now, typically, if we talk about a passenger vehicle, that emits about 4.6 metric tons of carbon dioxide every year. And in fact, when we talk about cars and trucks, these are producing nearly 20% of world's greenhouse gases. And on the other hand, a vehicle that operates exclusively on electricity, that is known as electrical vehicle, or hydrogen fueled vehicles, that will not emit any tailpipe emissions. That is there. And that is the reason that most countries are targeting non-zero emissions from the vehicle by 2050. And most of the countries are shifting to either electrical vehicles, and nowadays, of course, they have started working on hydrogen fuel also. Initially, that was not there. There were reasons for that, because when we talk about hydrogen, people have been working on hydrogen for quite a long time. I know even Professor UN Srivastava was there at BHQ. He was working on hydrogen fuel-based vehicles about 30 years ago. That was the time when I met him in the department. But that time they were working on hydrogen fuel-based vehicle, but that was based upon combustion engines. Right now, people are not working on combustion engines. They started working on fuel cells, because with fuel cells the efficiency is going to be quite high as compared to what was there when we were talking about the combustion engine. So that is the reason that even though right now most of the commercially available vehicles, the new vehicles which are coming up are electrical vehicles, but people have also started working on hydrogen fueled vehicles. See, when we talk about hydrogen fueled vehicles, still we cannot say that we talk about hydrogen and that is always going to be something which is not going to give us pollution. It is only when we talk about the hydrogen has actually been classified into various colors, and that does not mean that hydrogen is colored. This is actually the way you produce hydrogen. So we talk about green hydrogen or blue hydrogen or black hydrogen or brown hydrogen or pink hydrogen, red hydrogen. All these are the classifications of hydrogen. But most important is to produce hydrogen that will not produce any pollution, and that is going to be either the green hydrogen or the blue hydrogen. Why I'm saying green or blue? Because green hydrogen is produced through water electrolysis. That is a process whereby we are employing renewable energy only. And obviously, because when we talking about using renewable energy for producing hydrogen using electrolysis, that is not going to produce any air pollution. Blue hydrogen, of course, it is sourced from. One is trying to get this blue hydrogen in refineries where we get we have lot of hydrocarbons, but then is whatever CO2 is produced, that is actually captured, and so we are not releasing CO2 in the atmosphere. That is why, although it is not as good as green hydrogen, but still it is fine. On the other hand, if I am talking about gray hydrogen or black or brown hydrogen, there are problems with that, because when we try to produce hydrogen using those techniques, that is again going to give us the air pollution. So if our source is going to produce air pollution, we are not going to reduce air pollution, because the purpose of air pollution, and if that is not happening, of course it is not going to be a very useful technique as such. So if we require pollution free world, one requires green energy for transportation. That is one thing. And when we talk about green energy, even when we talk about electricity, we cannot say that it is green, because even when we talk about the normal electricity, in India, most of the electricity that is being produced is not only in India, I think world over, most of the electricity that we produce is from the thermal power plants, where we are using coal, we are burning coal, and that is again producing air pollution. So one has to look for green energy, and when we talk about green energy, one going to be the sun. See, otherwise also, if I'm talking about transportation, fossil fuel availability is definitely going to reduce a lot in future, and that is the reason most of the vehicles are expected to be either electrical vehicle or hydrogen fuel vehicles by 2050. That is what is expected, and most of the governments world over are giving lot of incentives for these things. In India, means some of the states, not all the states, but some of the states are offering subsidy for installation of electric vehicle charging stations to the extent of 50%. I know Himachal kinds of incentives, and if you talk about a country like USA, recently they have sanctioned the grant of $7.5 billion for next 5 years for this purpose. So a lot of incentives are being given by the countries world over, and so most of the vehicles, as I have already said, are going to be electrical vehicles, because that is a technology which is fully developed. When we talk about hydrogen vehicles, there are still some problems. One is still not very sure about the safety when we talk about hydrogen vehicles. That is one. And second problem is the fuel is still far expensive than when we talk about using hydrogen vehicles, and that is the reason for at least next 15-20 years, what we expect is that EVs will be more popular than the hydrogen fuel vehicles. Maybe later on, the cost comparison can be such that even hydrogen fuel vehicles become more viable. Now, important thing is, when we talk about implementation of electric vehicle policy, one has to enhance the production of electrical energy. And if I'm talking about a country like India, whatever we produce now, probably the energy requirement is going to increase 10 times in another 20 years. And when I say 10 times, it is not just the production of electrical energy. One has to talk about the other infrastructure also, which has to be there. The transmission, the grids, all those things we need to enhance a lot. And second important thing is we also don't want pollution. So that means electrically generation has to be using green technologies. Now, when we talk about green technologies, again, this is some calculation that I made, that if I'm talking about a car, generally a car will have a battery which is 60 kilowatt hour, and obviously if that is charged with a 60 kilowatt hour battery charger, that is one that will charge that. That is what is expected. If I want the car to be charged in lesser, maybe I have to use 120 kilowatt or 150 kilowatt battery charger. Then another important thing is, if I'm talking about something like 50 crore vehicles, that energy requirement will become as high as 3000 terawatt, and presuming that only that 1/10 of vehicles are being charged at a given time. And obviously, if I'm talking about 3000 terawatt, right now what we are producing is only about 350 terawatt. That is the reason I said that energy requirement is going to be as high as 10 times whatever we are actually generating now. So these are some of the figures which tell right now what we are doing, and we can see that if we are using renewable energy sources, we are using it only for about 25%. Nuclear, anyway, it is quite small and nobody is interested in using nuclear energy. Hydrogen is also not that big. Mainly it is coming from thermal sources. And obviously, these are the problems that I've already discussed, which are going to be there when we talk about that much energy requirement. And as I've already said, that one has to go for the green energies. But green energies, again, there is a problem. If I look at that, is quite high. It is in 1 hour we can produce. We actually get more energy than that is required throughout the year for the whole world. On the other hand, energy from sun can be converted into electrical energy. We can either use photovoltaics, the solar cells, or solar thermal power plants. That is another option on which people are working. And then, of course, when we talk about hydrogen vehicles, that is again a solution. But for producing hydrogen, you will still require one major problem is energy is available only during the daytime. So, and when I talk about daytime, it is only 6 hours, mainly when we can actually convert the energy that is available from sun into electrical energy. And if that is so, we are trying to produce a lot of energy from that. That will actually create a big imbalance to the grid. And 50% of electrical energy, if that is produced using photovoltaics, it is actually going to create problems if you don't store that energy. So one option is to charge batteries. That means we have big battery banks, and during daytime we charge batteries, and during night time we discharge that to meet our requirements. That is one option. And another option is to use solar thermal power plants, where one can talk about chemical energy storage. I'm not going to talk in detail about that because that requires full 1 hour to explain that part. But that is another option. When we talk about battery storage again, if I talk about a normal lead acid battery, its lifetime is quite small, 3 to 5 years. So replacement cost is going to be quite expensive. That is what one has to look for. Second option is whatever they are using in vehicles, using lithium-ion batteries. Right now, those are quite expensive. So again, one has to really look for some economical way of doing that. And lot of research is going on into new technologies for batteries. See, in fact, last year only, he got a Nobel Prize in chemistry for lithium-ion batteries. So we discussed with him that this is the problem that if we talk about lithium-ion batteries, these are going to be expensive. What are going to be the options? So he said one thing that was quite interesting. That is, when they are working on lithium-ion batteries, lithium is a light metal. In fact, they are trying to produce batteries which are extremely low in weight. So if you talk about weight to energy density, basically energy density should be quite high. Energy density to weight ratio should be high, and that is what they are actually working on even now. And the reason for that is they want to use those batteries for aviation sector. So that is the reason they are working on that. But on the other hand, what he suggested was that if one is really interested in storing energy and using it, that means if we talk about the fact that what we are trying to do is we are looking for something where we are looking at a stationary application. We are not moving those batteries. Then the ideal solution is go for sodium-ion batteries. So sodium-ion batteries are going to be quite cheap as compared to lithium-ion batteries. What you require in sodium-ion batteries is primarily the electrodes are mostly carbon and a few more things. So that technology is reasonably economical. In fact, one of our colleagues is at IIT Kharagpur. He has made very good sodium-ion batteries, and they're still working on that, planning to commercialize that now. Things are certainly going to be such that we work on those batteries. Life of those batteries is going to be reasonably good, and are going to be much more economical. And if that happens, probably storing batteries can actually be a very good choice in future. So that is what people are trying to work on. That means people are working on the battery technologies a lot these days. So that is one area where many people can think about working. And but there is another option. That is solar thermal energy. So that is they heat some of the salts, and but of course the heat capacity of those salts should be fairly high, and then also we can use the solar thermal power plants, and we can store energy in the form of heat and then use it for producing electricity during night time. That is another option. We can also store energy using green hydrogen. If you produce a lot of energy, you can convert that into hydrogen, and then we can use hydrogen at any time using fuel cells. That can be one option. So all these options are certainly there when we talk about energy and energy storage also. Right now, if we talk about fuel cells, I was just going through that literature recently. 1 kg of hydrogen, it can run your car for about 300 kilometers using fuel cell technology. So that is the reason they are working a lot on fuel cell technology, so that the cost can be cut to a point where it is almost comparable with at least the internal combustion engine based vehicles, or even the EVs. Because EVs, there is going to be another problem also, because you need to change batteries maybe after 7-8 years or so. So that is another cost which one has to take into account. So maybe one is trying to look for economics so that things can actually work when we talk about EVs or hydrogen fueled vehicles. So this is the principle of the solar thermal power plant where we use a parabolic turf in the form of mirror and then heat salt water and all those things, so that things can actually work. So these are, so I think I'll go through these quite quickly. So finally, what we can do is, when we talk about green energy, energy storage is an area where lot of new developments are actually taking place. And because if one has to take care of the environment, one has to work on those things. Of course, if one is working on these areas, most important aspect for any researcher is that this area has immediate commercial value and can be used for society. And when we talk about these areas, particularly renewable energy areas, lot of incentives are available from various ministries, whether it is MNRE, and when we talk about these ministries, they are giving lot of incentives not only for academic research institutions but also to the industry. And if we talk about the new scheme that they're talking about, the National Research Foundation, what they're actually expecting is that only those researchers will be given grants who have a collaboration with industry. That is one theme that Government of India has come out with. And obviously, one has to work in areas which will have some commercial value, only then an industry is going to support you. So these are the areas which are going to be quite useful for any researcher, whether it is in physics, chemistry, or any other science also, where one is trying to work on green energy in particular. Thank you very much.
Thank you so much, sir. The talk was really very insightful. Now the floor is open for questions. Now I would like to invite Dr. Anirudh Joshi, General Secretary, GGVSD College, Chandigarh, to join us and deliver a vote of thanks to the chief guest, Dr. Nadeep Kaur.
Proposing a vote of thanks to a friend like Navdeep Goyal, who was a student when I was a very senior teacher in PU. He became my colleague, then we became colleague in arms when we tried and successfully tried for pension for PU teachers. We used to go to Delhi to meet authorities. He was our driver. If we would request him to share the petrol prices, he would say, no, this is the cause of the teachers. I'll not take any penny. A lovable person, a good scientist, an affectionate student and colleague. Thank you, Nadeep, for being here. Nadeep has talked this morning of pollution, vehicle pollution. Should we go to the bullock cart age or cycle age? No. Alternatives suggested by Nadeep. I'm not a great fan of this non-pollutant and ending the carbon dioxide. I don't think we can eliminate carbon dioxide from this universe. Whatever we do, I'm not a science student, I've been a Sanskrit student throughout my life. I read somewhere when I was in school that the trees emit carbon dioxide in night. And they give oxygen during day. Human body is such a body where carbon dioxide is being produced every day. There are other fields also. So what's the solution? Solution is reducing its quantity. The way we should do it, humanity is going to prosper. We have to live. There are paradoxical situations. The biggest votary of this non-pollutant things is America. And the biggest user of petroleum is America. The number of vehicles they have, the number of factories. I don't know how photovoltaic cell is manufactured, but I think there is energy used in it which comes from carbon dioxide. I'm not a science student, I may be wrong. So you can't do without that. You have to reduce it only. You have to fix a limit. About 20 mantras in Rigveda talk of pure air, Shuddha Vayu. They prescribe daily havan for it. And Guru Nanak Dev Ji said, Pavan Guru Pani Pita, Mata Tartma, Divas Raat Dayal, Khele Sakal Jagat. You have forgotten that. We have forgotten why we used to worship Vayudev as a god. Why we worshipped sun as a god. Evolved forward. If you eat the food like that we are eating these days, not cooking at home, opening the package and eating. There's a principle in economics. Make the society consumer society. What will happen? Business will flourish. How do we make those things which are packed? Every packet you have to produce carbon dioxide somewhere. For vehicle, we can control it. The vehicle has given so much about it. About physics, I think there has not been a single day that there is not a new challenge in physics. Recollect rather. Dr. Homi Bhabha came to Punjab University when we were such scholars. I listened to it. He said, no pace, no speed is enough for research in physics. Students of physics, teachers of physics. Keep yourself abreast with what's happening around the world. I was remembering, few years back I read about dark energy. कोई होती है ये? Dark energy. Now we are thinking of white energy. We were very much excited when Bhakra Dam was constructed. Hydroelectricity has its own limits. पानी आ गया तो हो जाएगा, नहीं तो नहीं. Thermal fuel is coal. They have a limit. The storage has a limit underground. So has the petroleum. So we have to worship sun. Holy, holy. Please do something more for humanity. Isn't people? Our body also talks about energy. And there is spiritual energy also. I'm remembering one of the schools of philosophy in India is called Nyaya philosophy. They say this word is not made by God, but by the atoms. They are called Pramanuvadi in philosophical terms. Everything comes from the atoms. They have no big labs like us. They have nothing. Astronomy, study of sciences with bare eyes, no telescopes, no nothing. But the movement of every star, every planet, they have recorded. Take Jyotish. They'll tell you सूरज कितने बजे चलेगा, चंद्रमा कितने बजे, बुध अब कहाँ जाएगा. They did it. Physics scientists should do it also. Thank you, Navdeep. Thank you. Thank you, good guys.
As we embark this enlightening journey together, let us remember the words of Nelson Mandela. Education is the most powerful weapon which you can use to change the world. Let us embrace the knowledge and wisdom that this seminar offers and strive to make a positive difference in our fields and in our society at large. Our first speaker for today's session is Dr. Sumendu Jana, an associate professor at the School of Physics and Material Science, Thapar Institute of Engineering and Technology, Patiala. He finished his PhD in 2008 from Birla Institute of Technology. He has worked with CNQO Group in United Kingdom. Dr. Jana's research interest includes nonlinear optics, photonics, and nonlinear dynamics and laser. Sir was engaged in a number of research projects, including moving and colliding cavity solitons and cavity soliton molecules funded by UGC BSR in the year 2012 to 14. All optical cryptography using localization and dynamics of photon in semiconductor microsonators funded by Sir 2020 to 2023, and many more. Also, he has been a member of Optical Society of America. He has written about 40 research journals and has been awarded by Boycast Fellowship and Visvesvaraya Fellowship. We are pleased to have you, sir. Let's welcome Dr. Sumendu Jana with a resounding applause.
Good morning, everyone. Thank you for calling me here. This is a great opportunity anyway. My topic is this one that actually what happens when I started learning physics. Very recently I started learning physics. Before that, I was just trying to memorize all these things and trying to get exam. So I started feeling that we should learn physics or whatever is happening surrounding us in our own way. So this talk is basically to that purpose. Okay. And yeah, this is. So if you see the syllabus of worldwide, anywhere you go, if you see the syllabus, here I picked a syllabus from the CBSE class 12. My daughter is in class 11 now. So if you pick that syllabus, BSc, MSc, everywhere, classical, quantum, whatever you are doing, first they will teach you the harmonic oscillator. Even in our engineering science also, engineering science, everywhere we are starting, or some portion of harmonic oscillator will be there. Now my question is, in fact, my students' question is, why on earth I will learn harmonic oscillator? Is there any benefit out of that? So even I can ask you, what is the benefit of doing or learning harmonic oscillator? However, I will not confine myself within harmonic oscillator. I will go beyond harmonic oscillator. But harmonic oscillator is the core. It is at the heart of any syllabus or any kind of that academic activity. So meanwhile, you can think, and I am showing you this one. This is a self-explanatory slide. You can see several examples of oscillations which are you can consider harmonic. Okay, and I hope you all know the bookish definition of harmonic oscillator. And from there, some kind of deviation we are trying to learn every day. We are using every day. So starting from the tuning fork, probably you are not very much familiar with tuning fork nowadays. Luckily, I saw one tuning fork during my college life. This is you are very much familiar with, and already you got an announcement. Keep your phone in the vibration mode or something like that. So this is LCR circuit and the pendulum anyway. This is a moth or insect above the water surface which will vibrate its wings, and you can see the waves. This is, our heart. You can feel it. It is always beating. And this one is on chemical reaction, BZ reaction, and this is the molecular vibrations. So everywhere one thing is common, the oscillation. Okay, so my today's topic is basically on that oscillation. Although I told that it is harmonic oscillation, but not always that will be harmonic one. Now question is, you can get this type of oscillation everywhere. Okay, like this is another example of, I'm giving you scattered example anyway. You can add many others here. This is the Tacoma narrow ridge. It's a very important example of non-considering harmonic oscillations or damping caused by the air gust. So in Tacoma narrow, there is a small passage just after few minutes of the inauguration, the bridge was collapsed because they did not consider the damping of the bridge. And here, this is the devastating view of the earthquake, where again the vibration is very much. I'm not saying they are always harmonic oscillation once again, but that vibration is very much related here. You can find vibration almost everywhere. Those who are musicians, they know it very well. Okay, even without being musician also, you can understand that vibration is very common in all types of instruments, musical instruments. It can be a string instrument, it can be that membrane like this type of instrument, the drums and everywhere. Okay. And the animal world, they use vibrations, better to say they use waves, how they are creating that waves from vibration. If you can create vibration surrounding media, there you will find some waves. So you know all these things. So it is very common in case of animal world. So the bat, it will send a wave which will come back, reflect back from the prey, and then the predator will catch that one, and the dynamic process will go on. So using that one, they can catch their prey or locate their prey, and we are trying to copy. Human being, we are trying to copy that technology. We are using sonar and other things. Okay, not only sonar, we are using this technology. We are using in sonar. Although you can find this technology in, Amazon and other e-commerce. They have their warehouse. There are so many robots are working. So they are communicating with each and with one another using that kind of sonar-like technology. So they are using waves. So with vibration, I will use also wave because they are very much related. Okay. Now you say me, what is the use of learning these things? I know they are there. I know there are harmonic oscillations, anharmonic oscillations, damped harmonic oscillations, and many other harmonic oscillations, varieties of harmonic oscillations. But what is the reason we are learning these things? Why we are learning that? Are you convinced? One cause is, yes, this is in my syllabus, so I need to learn this one. That is the prime cause. Done. But other than that, why should I learn harmonic oscillator? Anyone? Okay, so please, you can interact with me. Okay, anytime. Anyway, when you are thinking that time, maybe you are a little shy, so don't be shy. You can interact with me. Just try to feel that why we should learn harmonic oscillators. Okay, it is everywhere, almost everywhere. But what is the use of that? That's why deliberately I gave that title, that how much I can earn. So, do you feel that I can earn something?
Okay, meanwhile, when you are thinking, take me, this I borrowed from my kitchen. So somehow I mixed all these pulses. You can see here, can you see this? I have moong dal, green chickpea and some yellow peas. All these things are here. Somehow I mixed it. Now, how you can separate them? Can you do that? So I'll open it, I'll spread it, and one by one, should I pick it? How you can do that? No prize for this. Okay, do one thing. Just give a vibration. Okay, try it. Jaldi ho ja baba. Try it, and then you will find in the morning I tried it twice. So finally you will get, this is your common day-to-day experience, you will find that the heavy particles, the bigger one, they are coming at the top. So instead of these, if you apply it for some other particles where they are very much mixed, so you can separate them out. So at least this activity is showing, I hope it is showing, that you can do something using the vibration at least. Okay. Now, this type of vibration, this type of technology you need to develop, you need to learn that how I can use that vibration and how I can smartly take advantage of that oscillations or all these things. So I'm trying to give you some examples where we are using vibrations, oscillations, and then of course waves. Now, if you go to the subatomic state, to the massive, the universe and others, everywhere, one thing you will find common, that is the vibrations or oscillations. You can go to nucleus, atom, molecules, and then you go to the bigger size. So everywhere, this this slide can give you that what kind of vibration you are getting, what different types of vibration you can get. One by one, we will find them. Okay. Before going to that, let me give you some example. Why vibration is common everywhere. You can see vibration almost everywhere. Let me give you an example. I'm tapping, or whatever I'm doing. You are getting some sound. Why? I'm just hitting this one. It's a linear force. But instead, what I'm getting a wave. Why I'm getting a wave? Because this thing is vibrating. Okay. Due to the vibration, the surrounding media that will vibrate, that will create a wave, so you are getting that. Okay. Now, one more thing. I'm giving another force. This you are familiar with. Okay. So this is the equilibrium position of the pendulum, and I am giving a force. So if I release, what it would be? It will come here. It should come back here. But it will not do that exactly. It will go to the other side, and automatically you know this thing very well. So it will show you some oscillation, and eventually it will come to the equilibrium state. So whenever you can think, imagine any kind of such thing. Most of the cases, whenever you are putting some force, kind of oscillation you will find. Okay. And why we are getting that oscillation? May I ask you this question? This is the equilibrium position. Okay. I am giving some force. If I release that, it should come back here. Why it is going to the other side? Just think. I'll just take it here. I'll release. It should be here. Why it is going to the other side? So anyway, you can think about all these things. Very simple one, but I need crispy answer. Anyway, so this type of oscillations are very much common. My question is why they are very common. Probably we are trying to get stabilization. In order to get stability, probably we are doing such oscillation. On a tightrope, yeah, that thing is there. You are familiar with that tightrope walking, and when you walk, not you, some people when they walk, they just try to balance themselves like that one. Vibration is very common. Okay, and that flag, when you see that flag, will show you oscillations. So almost everywhere, main target is to get the balance, get the equilibrium. To achieve the equilibrium, you are trying to oscillate. So whenever you are boxing somebody or whatever, you don't box anybody anyway. So whenever giving some force, oscillations is very common to that. Okay. Are you convinced or should I continue this one? Now, some scattered example. In the molecular world, you will find different type of oscillation. Okay, there may be oscillations like this, linear. There may be twisted oscillation like this. There may be combination of that. Now, for all, you will get some different signature. For example, do one thing. Let there will be a light. Okay, and I am oscillating like this. So my shadow will show you something. If I oscillate like this, twist like this, my shadow will be something else. So those two signature will be two different things. By observing those two signatures in the shadow, I can differentiate that what kind of dynamics, what kind of oscillations I'm seeing. So depending on that, you can go for different type of spectroscopy. However, that spectroscopy is not that easy, what I'm showing you. It will be definitely complicated, but at the bottom, they are like that. So different types of dynamics, and those dynamics are basically oscillations. Okay, rotations. And I'm not considering oscillations and rotations in a different footing. If you are rotating like that one, and if you take a projection of that, it will just oscillate. So they are in the same platform I'm considering. Okay. Now, how important is this? Depending on different oscillations, you can have different spectroscopy, and it is $1 billion industry. The data what I am showing you, this is old data. I did not update my slide for a few months. So this is old data. And believe me, the market has been raised. Okay, so it's a huge market depending on the oscillation. If you know the oscillations, if you know the characteristics of all these different atoms and other things, and if you can utilize it smartly, then definitely you can enter in that industry. Now, this one I will not go deeper. I am not at all expert of this, but we know that there are different type of vibrational states, rotational states, and depending on that, you are getting different energy levels. So when you learn that nuclear physics, there you find all these different models, shell model, collective models. There you find a bit complicated type of oscillations. Okay, so and then this is rather common to you. I hope you are masters and BSc students, so you know the dipole oscillations. Okay, so how you are getting that electromagnetic waves? There are different ways to get those electromagnetic waves. Okay, so one way you just getting as you just have an oscillating dipole. What I am showing you here, all these figures you can get in Wikipedia. So very common figures. So these oscillating dipoles will create a wave, and if you are going for higher order, the quadrupole, octupole, you will get different type of vibrations and different types of waves. And depending on that, so many study people are doing till date. Okay, so this is another branch I am trying to point out. And this one is much familiar to you. Oscillating circuit, you have L and C, capacitance and inductance. Okay, and you know if you are giving some charge, you are charging the capacitor, then release. Okay, then what will happen after highest charging? It will get discharged. That energy will be stored in the inductance, and this thing will oscillate for the for infinity ideally, but actually it will not happen because there will be resistance. Now, this common thing where you can use, this is very common topic in your syllabus, so where we can use it. Even in your book, it is given. So these are the applications. The most interesting application to me is the Shinkansen, the bullet trains. They have different, you know, Japan has different generation of bullet trains, so-called bullet trains, Shinkansen, Hikari, all this. Now, if you apply the conventional brake there, what will happen? The two metallic thing, the shoe, brake shoe, and the wheel, they will just stick. You cannot take them out. So it is not possible. So without touching, without physical interaction, you need to apply brake. So there we are using actual damping, electrical damping we are using. And what kind of damping? The harmonic oscillator, the damped harmonic oscillator, what you learn? Similar type of damping we are applying there using electrical, that LCR circuit. Okay. So electrical clutch we are using, and many other applications of such electrical damping you will find in your day-to-day life. And this is much more common. This list is very common. We all know that swing and different oscillators. I listed several oscillators: playground swing, double pendulum, Foucault pendulum, Helmholtz resonator, the tuning fork I showed you, vibrating string, different type of vibrating strings are there. So board string, Strut string, Clark string. So all these everywhere, depending on the action, you are getting same string. If you are plucking this one, striking this one, and if you are rubbing that one, you will get different sounds, different quality of sounds, different vibrations you can get. So why you are getting that one? You need the knowledge of oscillations, you need the knowledge of that damping and all these things. Now, here I just enlisted those, but you can pick any one of them. Its application, huge application you'll find. I just showing you one. Okay, so before that one, do you know what is this one? That figure. That figure here. This is vibrating vigorously, not this one. Here somehow we used one vibration cancellation technology. So you know oscillations, you know damping. Now here we are applying that what kind of damping we should use so that the oscillations, I can cut that oscillation. And in earthquake prone region, particularly in Japan, they always take care of this type of vibration oscillation. This type of vibration oscillation using string and other damping material, they do these things. Several practical examples you'll find in industry and your day-to-day life. In optical lab, you will find you need vibration isolation. Even if I work, the optical instruments, they will be disturbed. The data you cannot take properly. So there you need vibration oscillations kind of damping. Actually, this table is literally floating on air. Okay. And this is the generator, 1, 2, 3, 4, several generators are there. So all of them will vibrate in their own frequency. Now they will interfere with each other. I am vibrating with my frequency. The second one is vibrating with his own frequency. Then there will be interference. And how to place them in the same room? You need to apply some vibration oscillator. And this is very, very common challenge for any engineers. Okay. For example, the big buildings, Burj Khalifa, or maybe not Burj Khalifa, any simple building, there you will find huge number of transformers are placed in the same place. So you need huge space, huge gap between them. In order to minimize that space, you need to apply vibration oscillator, isolator, and other things. So there your knowledge of that harmonic, enharmonic, damping will be helpful. Meanwhile, you can give me some example also, so feel free. Here I am picking just one oscillator, which is called parametric oscillator, and you can see its application many here. This slide is just copied from Wikipedia. So you can see this slide, no need to go to the details of this. Parametric oscillator, you change the parameter of the oscillator system, you will get resonance at different situations. We can use this many here, including that conversion of audio to radio waves. In laser, we use parametric oscillators. Many here use that parametric oscillator. And one of the easiest example of parametric oscillator is the playground swing. So that simple one can be applied in very sophisticated and serious applications. Many here, okay? So this one, nowadays people are very much crazy about Chandrayaan and all these things. So in like Earth, there also in Moon also there will be quakes. So that lunar quakes, moon quakes will be there, and there you will find two different type of vibrations. So the knowledge of vibration is very important there also. And this one is Rayleigh wave. You can see the structure, the effect will be something like rolling. And here there is another very interesting name. They give it love wave. I don't know what the name is. So there you will find this type of zigzag waves. The two waves you can find in the lunar quakes. And from the very beginning, from the Apollo mission, people are trying to quantify what kind of vibration is happening there. So they are trying to understand the dynamics of the moon and other things using that vibrations, basically using that vibrations. And this one is, I hope this is familiar to you, astronomical. From small one, I started with atoms, molecules, and then I'm going to bigger world. you are familiar with this type of picture, we call it binary stars. There also you'll find kind of vibrations depending on their structure, their infraction, and all these things. And it is very common in terrestrial, the cosmic objects. Those objects, they show you kind of vibration. It may not be that type of pendulum one. Their shape, their size, they can periodically oscillate, something like this, not that simple anyway. So many oscillations are there. Now coming to the chemical world. Meanwhile, if you have any idea, any example, if it is coming into your mind, you can share with us. Okay, so there is one family of chemical reaction, Balasov-Jablonski equation. This is little tongue twister, so usually I say BZ equation. The 2-3 things you mix up, and what happens? This type of, this is one example. This type of thing you will find. Just watch what is happening here. What is happening here? Sorry. The color is changing periodically. You can see that blue, green, red, that color. Just point, just watch at a particular point, you will find periodically that color is changing. Now you may say me, why, what I will do with that? This is really interesting, but what I will do with that? Okay, in that system, if you add some foreign body, any adulteration or anything, the periodicity will change. So by knowing that what is the change in periodicity, all these things, you can calibrate your system. And from that, you can find what amount of adulteration is there, what kind of particles, foreign particles are there. So very direct application of that thing you can find. There are huge numbers. You are having mobile phone. Okay, so you just search BZ equation. You will find different types of such BZ equations. Some are creating two-dimensional patterns and all these things on a Petri dish. So very interesting one. And what is the common, the underlying thing is there you are getting some periodic, some oscillatory thing, and that is dependent on the, definitely on the system parameter. It is dependent. Okay, many other. I am not going to that. Just on one thing, you just see. I am giving you several reactions and all these things. I personally don't know those reactions very much, but what attracts me very, that is the with time you see the potential, the chemical potential and other things that is changing periodically, and that periodicity is very much sophisticated, very much depending on the system parameters. Now coming to the biological system, our brain. So inside, what is happening? Forget that. Just count how many oscillators I am writing here. Molecular oscillators. This is cytoplasmic oscillators. This is electrical activity oscillators. And here we have another picture of that redox oscillator here. Transcriptional, translational oscillators, membrane excitability oscillators, all these oscillators are present in that brain. And those who are familiar, they are saying many more oscillators are there. And their periodicity, that will depend on your system needs, the parameters of your body and other things. How much input you are giving, what is the time, how much fatigue you are, so many physical parameters, they will decide the periodicity of the oscillators. And not only that, like you learned coupled oscillator in your lab, they are also coupled oscillator, but very much complicated. Okay, so another example of that. This is a gene circuit. Okay, so you can see with time how the protein level inside the gene is changing. Interestingly, I gave you the research paper who just proposed this one. If the number of genes, here I have 3 genes, so there you will get periodicity. Please follow the color. This is this one, this one. The periodicity is like this. If you have genes, what is the periodicity? And you can see if you go through the paper, you'll find for different number of genes, the periodicity will differ significantly. So from that periodicity, however, this is not very easy to find that periodicity, but if you can, from that periodicity, you can find the activity of the gene and you can characterize them. So It is there, but not only oscillator, many other things you need to know. But the key idea is oscillator. I was talking about the coupling of them. So you can see all these couple oscillators, how they are. This is oscillator 1, oscillator 2, what we are familiar with for mechanical cases, but here you can find them in biological cases also. No need to go to the details, but at least one thing is very common. We find they are oscillating periodically or slightly aperiodically. That deviation will be always there. Okay, ideal thing is the boy will be like this, the girl will be like this, but practically we are not like that. That is good anyway. So you need some deviation, and this is a phase plot. Phase plot is nothing. It's location versus velocity if you plot. So you will get kind of this type of trajectory. If it is periodic one, you will find closed trajectory. That's all. So periodic oscillations, maybe harmonic, maybe little anharmonic, is very common anywhere you go. Okay, these are all scattered examples. Let me skip all these things. Do you like some mathematics? Little bit. Jada nahi patayenge. Okay, so what is this one? What is this one? You all know this. Try it. I showed you this thing. So you are, don't forget this. Anyway, you just displace that bob, it will come back. So the restraint force I know, this is a harmonic oscillator, very much ideal harmonic oscillator. Now practical systems are not that ideal one. Just one question, no need to answer. We ask simple harmonic oscillator. Just ask yourself, what is the simplicity in that simple harmonic oscillation? Okay, so very interesting thing is there. Anyway, so you take harmonic oscillator, but practical systems will always have some damping, some resistance. So there will be some damping. So this is the, where is the damped harmonic oscillator? This one is the damped harmonic oscillator. Okay, some other symbol I used, but basically this is the, that minus k by m, that part is this omega square, the frequency square I wrote. I hope you know all these things. And this is the damping part. Now, why I'm a bit interested in mathematics, how you will write damping. Think simply, you all ride bike or scooty with or without helmet. Please, with helmet. So, when you ride or you are doing pillion riding, so if you increase your velocity, the resistance of the air will increase definitely, the damping will increase. So, you apply just that idea here. With velocity, the damping will increase. So a damping coefficient we are using. So in the harmonic oscillator, you add one damping, your job is done, you are getting damped harmonic oscillator. What will be the change there? When you go for application, what will be the change? There will be change in frequency you all know. The frequency will be reduced. Okay. Now, please keep an eye on that frequency whenever you are talking about some waves and other things. You heard about the touchstone. There is a stone, fixed stone. Nobody invented it, but people say we also learn in story that there is a stone. If you touch it anywhere, the wood, plastic, it will become gold. Is that possible? Do you think that is possible? In story, there were no plastic. That time, plastic was not there, so only wood and other things were there. So if you touch it somewhere, the wood or whatever it is, it will turn to gold. Why it is not possible? We are doing so many marvelous things nowadays. Scientifically, it is not possible. Why? Please say me. Because you need to change the proton number, then only the thing will change. In case of wave, proton number, that is the soul you can see. You can understand that. In the periodic table, you know, the number is changing, you are getting different other elements. Now in waves, that soul is the frequency. If you change the frequency, the color will change, everything will change. Now when you are applying some damping, the amplitude is changing. Definitely the amplitude is reduced. But you compare damped and undamped, the frequency will be different, lower frequency. Now, if you go for other oscillators, you just check whether the frequency is changing or not. And the engineers, what they are doing, they are taking that. No, before that, one thing I should know, I should say, then I will go for that frequency one. Now, this is damped one, but it is not the full story. Sometimes, like I showed you that parametric oscillator, the swing in the playground, there continuously you are giving some external force in order to keep that oscillation going on. Okay. Now there you can say this is a driven oscillator. So in driven oscillator, what kind of force you are giving and all these things are there. Now different other variety you can find. For example, this is that X. X is linear one. Linear means its power is 1. Simply to say, if you put in something and if your response is following a line, that is a linear one. Now in some case, you will find non-linear one. For example, I need my pendulum now. Sorry, I need to show you that. Just forgive me, 1 minute. No. Anyway, I'm moving. No problem. So in normal case, you have pendulum like this. Okay. So it is showing you harmonic oscillation. But sometimes if you change if you increase the amplitude, what will happen? At some point, it will bend like this, kind of slackening you will find. That is the nonlinear portion. In mathematics, we write it in very complicated form like this one. We write it in this way. But it is not that. You all know that y equal to mx. Y power 1, x power 1. That's a line, straight line. If something is showing you other than that, it will be nonlinear one. Okay. So when your pendulum is showing you this type of, at the two ends, showing you this type of oscillation, definitely it is going to the nonlinear one. Now this idea you can apply anywhere, starting from laser and any other cases. The equation will be almost the same. Now those oscillators, due to that nonlinearity, you will find some new frequency in the system. So frequency is changing. Now frequency is changing means the color of that, if you are taking light, visible light, the color of that light will change. So using that, people can play with the colors and many other technological applications you will find. Second harmonic generation and other higher harmonic generation. And if you ask me what I will do with that, there are technological applications, like if you are going for multi-photon absorption and many other things, you can do scanning using those technologies. People are trying to use those in commercial platforms. Now, thing is, here you need to add, to take a good model, you need to add nonlinearity. Now here also, in the damping, you can apply nonlinearity. Who told that the damping will be always linear? There may be some nonlinear damping. So depending on these phenomena, your system will be little complicated. And for that, there are different oscillators. One is called Duffing oscillator. If your elastic part is nonlinear, you will find Duffing oscillator. If your damping part is nonlinear, you will get Van der Waals oscillators. If you are having both of them in practical system, both of them can be present. There you will find a combination of them, and they have practical applications. Okay, when in 1D you are seeing kind of oscillations you are getting. In 2D, when you are observing, you will find pattern formation. For example, you are familiar with Griffith's book. Okay, so electrodynamics by Griffith. You all know it, I hope. So there is a simple problem. The top, there are two slabs conducting surfaces, top and bottom. They are isolated, insulated, and there is a potential. There is a plate which is having some potential V. What will be the potential somewhere here? So you solve it using by solving the Helmholtz equation and all these things, and finally what you get? You get oscillatory thing. Why suddenly you are getting oscillation? I was actually demanding that thing. Everywhere you will get oscillation. Even there also you are getting oscillations automatically. The mathematics will give you the result is oscillation, and that oscillation is not like that. It is in 2 dimensions you will find kind of pattern you will find, and that pattern in practical life is very much widespread. If you go to the desert area, you will not find the grasses or the bushes only uniformly placed. You will find here, there, in patches you will find. Why that thing is happening? All these pattern formations, they are actual manifestations of these harmonic oscillations in 2D. Plus some other things are there. So you try to use little mathematics, what is happening and how I can write it in terms of mathematics. Then the understanding of oscillations will be very much clear. Okay, I think this is enough. And again, this is kind of Duffing oscillator and it's some interesting trajectories. And this is, you just don't go deeper. Just see, this is nonlinear Schrodinger equation. being used many here. Okay, and this is the Gross-Witkowski equation used in cold atoms and also in many other cases. Now see the structural similarity of these equations. They are all nonlinear oscillators. The same equations, if you know the solutions of this equation, you can apply it anywhere, only you need to know the underlying physics of that. So I just wish to give you some glimpse of that one. Now coming to some more interesting thing. How much time? 10 minutes. 10 minutes, enough. Okay. I think you heard about cellular automata. It is kind of, what is this thing? This is cellular automata. This is kind of motif pattern. And what is common among them? That motif is repeating after certain period. Okay, you can see this one, its period is 3. So you'll find 3 different motifs. Okay, so that will repeat. Here the periodicity is again 3. Here periodicity, I cannot count, it is 8. So I believe it is 8. Here I can count 4 different motifs are there and they are changing periodically. Now using that concept of cellular automata, people are doing many things. Okay, starting from biological world to the network, computation, many other people are using that. And the key idea is the periodicity of that cellular automata. And some examples of that, I'm not going to that. Conway's game theory. You will find application of game theory. Okay, just 1 minute I can devote for that. Using cellular automata, you can say that whether that cell will live or it will die. How many live cells are at its neighborhood? By counting that, you can finally decide that whether that plant or that living organ will finally die or it will live for that time. There you are using cellular automata, which is basically a periodic structure. Okay, now in living world, that kind of oscillations, not only cellular automata, any kind of oscillations or that waves you will find inside our brain. I was talking about Schrodinger oscillation, Schrodinger equation. People are trying to apply some part of Schrodinger equation in order to model the signal through our brain and our neural systems. Okay, so all these things are there. Now, these are the applications of cellular automata, and even people are so crazy. In some places, you will find the motifs of cellular automata, but these concepts, they are natural things. There also you will find the signature of that cellular automata, that periodic nature. I was talking about this type of pattern formation. Directly, you cannot find any connection between harmonic oscillation, anharmonic oscillations with this one, but it is there. How in 2D, 3D that pattern formation is taking place. This is one of the examples. Okay, and even mathematically you can find all these things. Okay, now I'm not very much philosophical guy, nor a religious guy, but one thing I followed, in any religion you will find this type of activity, around some burger debate or something like that. These are the Buddhist monks. They are from Morocco. They always, so that kind of rotation, that circulation, that periodicity. This is very common, almost everywhere. Why? Have you ever thought why this is very common? Earth is rotating, spinning. The molecules, they are also showing some kind of the electron, although that is not very correct. The electron is rotating, all these things. But that concept of rotation, circulation is almost everywhere. What is the philosophy? Are you trying to get stabilized? Are you trying to achieve the stability? Maybe that one. But this is very common, even in our practice. Okay. This is a Lorentz attractor. So, what is that one? You can find. Oscillations. You just feel your heart. If it stop oscillates, God forbid. But what will happen? We know. So that oscillations starting from jellyfish to everywhere. That oscillations. And even you can utilize this one because my topic was can we earn something? You just do one thing. Just feel your heart, feel your pulse. It may be 70 or whatever it is. Then you jog for 1 minute. It will be something. Jog for another minute. So from that you can have a model. Gradually it will be saturated. So you can create your own model. Using that by defining, you can create a small tool that will be very much helpful. that can be customized. So many interesting things you can do using that harmonic oscillators. So thank you very much for listening and for your patience. Any simple question? Okay, no tough question, please. Okay. I'm giving you some other example what I actually tried. Well, the cancer equation, there is a cancer equation. Meiosis, mitosis, so many things are happening. So how they are tackling that cancer? They are having some rate equations that how the number of cells, infected cells, good cells are changing, and then you are injecting extra that medicine you are. So all these things they are writing in terms of some equations, and those equations are kind of they are in first order, but they can be converted in second order, and they can be compared with anharmonic damped driven oscillator. So there we are using directly we are using the concept of harmonic oscillator. And what is the benefit? If we can solve them, actually we cannot solve them properly. We are taking approximation, we are taking that statistical approach. But if you can solve them, you will get solution of that system, which will give you what should be the dosimetry. Means for this patient, what dose will be there, what amount of medicine should be there, like that. Even you can predict that how long that patient will be there. Even you can apply some randomness, many different types of randomness, uncertainty, inhomogeneity in those systems. So what I showed you, those equations are very simple, definitely, but actual many complex and coupled equations are there. And for particularly for cancer and all these medical application, they are all delayed differential equation because you are applying medicine, it will take some time. Okay, so some delayed differential equations. People are using numerically, of course, there are softwares are coming, but at the underlying mechanism is the oscillator, anharmonic, nonlinear, and damped, driven. Okay, so it is one example what I tried. Okay.
Simple harmonic oscillator.
Why it is simple? Actually, to me, it's very much oversimplified thing. 3 absurd thing, please see it. So very much absurd thing. What you get, simple pendulum. It's a pointless, impossible thing. Hanging from a massless thread, impossible thing. From a frictionless, impossible thing. So all these 3 impossible, ideal one you are considering to oversimplify this because this is the ideal one. Practical system will be deviated from that. For ideal one, that will be the frequency. Now, what you are getting practically, it is bit deviated. From that deviation, you can find the nature, you can characterize that system. However, what I am saying, it is very much easy. It is actually not some complication. Okay, so that is my take on simple harmonic oscillation. But some other idea can be there. You may think you may share some other examples of harmonic oscillators on harmonic oscillators. Otherwise, you can give me thanks.
So I have a very basic question. So what is the difference between periodicity, oscillations, and vibrations? I mean, to a layman, how do we explain the difference between them, or are they the same for a layman?
Periodicity and vibration.
Vibration, oscillation.
Okay. So when you are vibrating, after a certain time you are repeating your structure. So that time that you can consider periodicity. I think it like this. So I am showing some kind of breather. Okay. In our research, we use breather. You take so breather. Okay. Some laser they show breather oscillation. Now this is my first condition. After a certain time, I'm coming back to that situation. So that time that you can consider that is the periodicity. So is that your question? Yeah, kind of that thing I can consider. Even people are using when you are applying it some pattern formation, they are not going to that restoring force and all these things. It is irrelevant there. If you are repeating some motive after some time, for example, we say this one. What is the frequency of that bus? One bus is going to Patiala, Amritsar, so every day. So that is kind of periodicity. There we are not talking about any restoring force. So people are even use those things in pattern formations and others. Actual pattern formation, that localization is everywhere. You know about gravitational wave and all these things are coming. You need to localize them. When you are applying quantization, quantum idea, you need localization everywhere. And you go deeper, everything will be finally quantized. We know electron, proton, not only that, there is graviton. Hopefully there is graviton. So there also you are getting this one. So we are talking about liquid crystal. Even there also you will find kind of localization of that periodic, little aperiodic oscillation. They call it nematicon. So everywhere you will find that localization you need to find. Now to do that, that anharmonic oscillations you need to do. Okay. Anything else? Please.
So how can a vibration heal the person?
How can a vibration
How can a vibration heal the person?
heals?
Yes, sir. Heals any certain disease that he suffered from.
Vibration. Had I demanded that one, that vibration can heal a person?
Sir, actually I studied about that.
Music. You're
Yes,
talking about music.
certain music or some sort of mantras that we usually say.
Okay.
To remove the stones, I think there is also some like vibrations, use vibrations.
Which one?
For stone, removing the stones.
In China, many types of bells are used for releasing.
Okay.
Bells are used.
Okay. No, I'm coming to his question.
With that frequency, they break that stone.
No, that is very common. You have that is very common. So first, I'm taking this example. Thank you. So you have low bladder stone, for example. Okay. So you can use vibration, not only one that will destroy your muscle. Several such vibration, they will focus there. That is very common. Thank you. So there you can use it. But what you are saying, some mantras and some chanting. Look, one thing happens when you are listening to some soothing sound, melody, that is exciting your brain, and from that some chemical locha, that chemical things will take place, chemical reactions will take place. That may help. Okay, and I think people are trying to learn that thing, to repeat that thing. Whether what is the difference between science and belief? That belief is anyway. I'm not going to that debate, but I am also having some belief. But science is every time you can repeat that one. So people are trying to find that recipe that okay, I listen this music and I'll get benefited. So there is a way, and people do meditation and all these things. But what is the equation? I cannot say that one. Maybe kind of resonance is occurring. Even we say in common words, आपके साथ मेरा wavelength match नहीं कर रहा है. What is that one? That wavelength matching is you need to be with that. You need to resonate with that. Okay. And I was talking about how to utilize that vibration smartly. Okay. So utilize that vibration smartly. There are different ways. If you have 1 minute, another demonstration. Can you start talking about among yourselves? Just start gossiping. Just please do it and listen what you are doing. Please, everybody, start listening. Start talking. Please do it quickly. Okay. So what you are talking, can anybody listen that one? No. So you are creating a vibration, you are talking, so some kind of wave is being generated. Now, I'll say 1, 2, 3, and please say Jai Hind. Okay? 1, 2, 3. Jai Hind. Thoda dheere. Even with the same loudness, you can listen this one. So what you used? You created the same vibration, same wave. But here, earlier there was no coherency. But now you used coherency. So by using coherency, you can extract force, energy out of that. You can do some work. So there are vibrations. There are many things you need to use it smartly. So that gives some answer of your question. But I'm still learning that thing. Okay, how that will help. Please.
Any book or resource that you recommend to study further about this?
Whatever you are getting, other than some fictitious thing. People say there will be aura behind, some pseudoscience is there. Please don't take it otherwise. We have electromagnetic waves in our body. Yes, that is true. But that cannot give you some aura here. It is not that powerful. So choose books which are popular. Just go to your library and keep your eye open. You will find several examples of that.
No, not example, but like proper oscillation and vibration. If I want to study those.
So many books are there. Pick any of them. All these standards books are there. Okay, sound, anything. You can find it. Any further question? No? Thanks.
Thank you so much, sir. It was really a fantastic conversation. Next, for today's session, we have Dr. Harleen Bhaiya ma'am, an associate professor in the Department of Physics, NIT Jalandhar. Ma'am has published more than 35 research journals in the field of quantum chromodynamics. She has published 2 book chapters, namely What is Inside the Nucleon in the year 2002 and Non-Perturbative Quark Asymmetries in the year 2011. She has worked as a principal investigator in number of research projects titled Chiral Constituent Quark Model and Proton Spin Problem in 2005, Hyperon Semi-Leptonic Decays in the Chiral Constituent Quark Model in August 2009, and many more. She has been coordinator of a number of national and international seminars. Ma'am has been awarded multiple awards such as DST Award in Germany in 2004. She was awarded as Young Scientist Award by DST in 2005 and year 2015. She was also awarded as Distinguished Young Scientist by Indo-US Science and Technology Forum and US National Academy of Sciences. Let us extend our warm welcome to Dr. Harleen Bhaiya as she takes the stage for her talk.
So thank you very much. So first of all, I would like to thank Neelu Mahajan for the invitation. And she has been a very close friend, and I feel very happy to be here and see all this. So I was looking this college website, and I was very happy to see that this college has been ranked among the All India ranking, and also this status of College of Potential for Excellence. And the best thing is, I saw that in the Department of Physics, they have diverse research areas where the faculty is working. So this is a very, I think, very proud, it should be a very proud moment for all of you, and the students should feel very lucky to be here. So, okay, to start with, so whenever we talk about science, so the thing is, many people are very scared of physics. So say physics is a very tough subject. So in general, in science, we should never fear anything, but science is just a little collection of ideas developed by this human race in the efforts in understanding the mind of God. So how the things were created, how the things are working, and so on. So the beauty of science in nature, so it is the most fundamental thing, and it is very, very beautiful. If you understand how things are working, in general, you can apply this to every aspect in your life also, and in the things you see around us. So if you understand the thing, so it gives us a new appreciation of the world around us. Okay? So, and also by understanding this, we can figure out these fine details in the universe. And also there are a surprising amount of unusual, which are yet to be explained principles that we encounter in nature. So you see, everything you see around you has physics. So as a physics teacher, I say each and everything, each and every concept, each and every process you see in the world around you, it has physics. So you can see diffraction, reflection, and all the things are there. Physics is involved, right? Optical illusion, physics is there. And science in everyday life. So you see electricity, force, friction. You combine all the concepts of physics and the things you see around you, each and everything. It's not just isolate anything. Every furniture, every gadget you have, everything you see around you is science, right? Physics, not science, physics. So now coming to the universe. So we know the things around us. As a physicist, what we seek is we want to understand how the things are happening, right? So as an engineer, you can say we want to know how this concept is there. We want to apply this. We want to make something new. But as a physicist, we want to understand how the things are happening and how it began and how we understand it now. So starting from the history of the universe, how it was created. So we all know that this Big Bang occurred, which created many fundamental particles. Fundamental particles means we cannot break them further. So these fundamental particles, which were quarks, they combined to make composite particles, neutrons, protons. So then, which further combined with electrons to make atoms, right? So then, because they were attracted to each other because of gravity, and then they collapsed together, created stars, and then the stars combined to create galaxies, and then in the galaxies, the stars exploded, creating carbon and heavy metals, and then we have this planet at the present. So to understand these fundamental quarks out of which this planets and we all of us are made. So this will help us to understand the early universe and will give insight into how our existence came into place. So this is the process I'm talking about. This is the point where Big Bang happened. And then from elementary particles to composite particles and then stars, galaxies, and this is the present time, right? So within the first few seconds of the universe life, so matter, it originated from a very hot and dense cocktail of this mixture of fundamental particles. And since the bond was very, very strong at that point of time, so the conditions were too hot and energetic to hold the fundamental particles. So that is why they were isolated. They were not in a composite form. They were isolated because the energy was too large. So then, during the first microseconds after the Big Bang, this contained a very hot and dense mixture of quarks and gluons. Now, what we aim is we are understanding the universe backward in time. So, see when you see this, I'll discuss briefly the history of our understanding of this present time to backward in time. So, we are understanding the universe, the existence of universe backward in time. Okay, so first you see you understood molecules, then you said, okay, molecules, they are made up of atoms. So our understanding is going backwards. But the occurrence happened in this order of time, but we are understanding it backwards, right? So I will discuss this God particle, existence of God particle towards the end also. But let me first discuss some elementary things. So then there are two questions which every scientist has been asking. So because of these questions only we tried to probe the things and understood the things. So what are the fundamental objects in the universe from which everything is made up of? Now we are saying we know about quarks, but when it started, the question when it started about 2500 years ago. So then it was, at that time there was a Greek word called atomos. So it was assumed that there should be some indivisible particles called the atomos. So then the second question is, how are the fundamental objects held together? How are they being held together? So there should be some forces which are holding them together. So this is the second question. What are the fundamental particles and what are the forces which are holding them together? So at the turn of the century, 1900, there were two fundamental forces known, gravity and electromagnetism, right? You are also aware of these forces, right? But then there are more. So once we understand these fundamental particles and what are the forces between them, we can construct a complete theory for this natural universe, right? But for that, we need to understand these things. So the science which studies these questions and is trying to answer this is called the elementary particle physics or the high energy physics, right? So elementary particle physics is called because we are trying to study the elementary particles, right? And it is also called high energy physics because, as I told you, that the particles, if they have to exist in isolation, the conditions have to be very, very energetic. So to study them, we need very, very high energy. So that is why it is also called high energy physics, right? So what is this high energy physics or particle physics? So this basically studies the elementary constants and the interactions between them, we have seen. So this is also called high energy physics because many elementary particles do not occur under normal circumstances. Okay? So we create them, or you can say detect them in very high this energetic during energetic collisions of these particles, and which is done using these accelerators. So I'll discuss a few accelerators also. So everything in this universe is made from the same building blocks of matter that is there, and also these particle physics, it studies these building blocks and works out how they interact. So let me tell you where this high energy physics falls. So you are aware of classical mechanics, which is used to study the macroscopic particles which we see around us. Then quantum mechanics, as to, you are postgraduate students or both? Okay. So I mean, I have prepared it that way. I mean, it's so quantum mechanics, is used to study the microscopic particles. Then there are some limitations in quantum mechanics, this non-relativistic quantum mechanics also. You formulate relativistic quantum mechanics for the particles which are moving at very high speed. So then in this quantum mechanics also like this equation, standard equation, Schrodinger equation is for one particle. You write the equation for one particle. So, but then we see there are particles being created and destroyed. So there is limitation for this relativistic quantum mechanics also. So there is a need to go to quantum field theory. So in quantum field theory, so we can we can explain how the particles are created or annihilated. So this particle physics is basically, there is relativity, quantum mechanics, but the theory is quantum field theory, right? So very briefly, I will discuss this. So history of atom. So we all know that you are aware of this. I just wanted to connect it to what we are understanding at present. So this in 460 BC, so it was like elementary particles were considered. You take a pestle and mortar and try to break the pieces. The smallest thing you get is called this indivisible particle. Then it was further developed, and it was found that atoms could sometimes eject a small negative particle, which was called the electron. Right? So things were developing slowly. So then atom, it was given this plum pudding model was proposed for that. But then again, there was this famous experiment, right, by Rutherford. So this alpha particles, they bounced back in the same direction, right? So this was a very incredible event that, he said that it happened, and it was like firing a 15-inch naval shield at a piece of paper. So only interpretation was there should be a solid positive core at the center of the atom where it is being repelled, right? So this was the picture. So okay, this is for this Coulomb interaction. So the particle close to the center only will show this reflection. So I will not go into these details, right? So then this Rutherford needed this alpha particles. You can have, you can ask, you are aware of these questions, I don't know, but you can look into these. So why did he need alpha particles to discover this? And then why do we need the huge accelerators to study particle physics today? So they are like connected, right? So now this was the picture. So there was a central nucleus, and it was having positive charge, and the electrons around this atom, they were being held because they are negatively charged, they are positively charged. But then again, this was not the end of the story. So electrons were discovered, and it was proposed that atoms are not elementary, right? Earlier we were proposing that atoms, they are elementary, but now we know that atoms, they are not elementary. Then also further, this orbital structure was proposed by Bohr. So now we have this picture of inside the nucleus. So we have protons and neutrons inside the nucleus, and outside the nucleus we have electrons. So the atomic picture is, we know the atomic picture now, right? But now again, then the question is, we have this nucleons. So are they elementary or not? Right? So protons and protons and neutrons, they are not fundamental. So they are further made up of smaller objects which are called quarks. So this was also discovered in this deep inelastic scattering experiment. So there was this incoming electron, right? This experiment, and it came into this proton, and then because of this scattering, then it was proposed that there are 3 point-like structures inside the proton, right? From this experiment. So 3 point-like structures means there are 3 quarks. It was proposed there are 3 quarks in the proton. So now you see, in order to see an object, the wavelength of the probe must be smaller than the object which is being observed, right? So we have this relation, and and to put the protons together, or for that matter any particles with some mass to put together. So this mass energy equivalence, right, relation. So we can concentrate, if we can concentrate enough energy at a point, so we can create some massive particle. I think this is being cut for this last line. Anyway. So particle accelerators, basically they can create matter from other forms of energy, right? So how we do that? We accelerate 2 particles towards each other. They have a lot of energy because of the motion, kinetic energy is there, right? Then we allow them to collide and annihilate to create energy or other particles. When they will collide, either they will create energy or some other new particles. So that energy can create any particle or its antiparticle with mass less than or equal to the total energy, right? So this is how we can create matter. So hadrons, right? Specific example if we see. So quarks are created from this initial annihilation. So you see, you have 2 quarks, you try to separate them. Those strong neutral forces, they act. So if you try to stretch them like a rubber band, so at some point this rubber band breaks, and at this point say it is breaking. So it is creating a quark-antiquark pair, and then you have 2 new composite particles. Earlier we had 1 particle, now here you have 2 particles, right? So okay, so coming to the picture, so protons and neutrons, they have quarks in them. So it all works out, right? We propose that proton has 3 quarks. So we give some quantum numbers to these quarks. So they have fractional charge. Okay. So some are positively charged, some are negatively charged. And if you try to sum up, like say proton UUD, which is having plus 2 by 3 minus 1 by 3. So the charge comes out to be plus 1 for proton, 0 for neutron. So till now it looks like it is working perfectly fine. So the quark model which was proposed, it told that the baryons and antibaryons, they are bound states of 3 quarks. And we have another group of particles, mesons, for which you can say pions, kaons. Pions is the best example for you. So they are bound states of 1 quark and 1 antiquark. Okay? So overall baryons and mesons, they are called the hadrons. Right? So we have a meson, so 2 quarks are there. Baryons, they have 3 quarks, and also there are some new species which are proposed, which are yet to be verified experimentally. So they are saying there can be a set of 4 quarks, mixture of quark, antiquarks, and so on. So, okay, so problems which came while introducing these quarks. So fractional charge, we are giving fractional charges to the quarks, so which was never seen before. And also is quarks, we cannot observe them directly. We have observed them and proposed them indirectly. We are saying that proton has 3 point-like structures, which we propose that, okay, there are 3 quarks. But we have actually not separated any quark or observed it, right? So we have proposed that, okay, there can be this quark with this particular quantum number, but they are not actually, separately they are not observed. So also, like proton, I said there are 2 U quarks and 1 D quark. So it appears that they violate Pauli's exclusion principle, right? Because U quark will have the same quantum numbers. So to overcome these limitations, so this color quantum number was introduced. So a quark can have 3 colors. It's not the real color, it's just a quantum number. So it can have 3 colors. So in that way, when you are putting 2 u quarks and 1 d quark in a proton, so those 2 u quarks will be of different color. So an additional quantum number is proposed for the quark. Okay, and also there are some you can say some rules also, like there are only these set of combinations observed, like quark anti-quark pair, 3 quark. It's not that you can combine any number of quarks with any number of anti-quarks also. So it is the combinations, they are limited. So this is color charge of quarks. So they have 3 colors, and this they are called color because when you combine, like it is red, blue, and green. So when you combine a certain number of quark colors, the overall combination should be a neutral one. Okay, it's not in real sense, but when you do some mathematics group theory, so there are the combination is a neutral one. It's like a singlet or triplet. I don't know whether you understand or not, but like it should be a neutral combination. So that is why only those combination exist which mathematically, if you calculate from the color combinations, they are coming out to be neutral. So this resolves the Pauli's exclusion principle problem. So now we have this picture. So we started with this atom. So then we said, okay, atom is nucleus and electrons are there around the atom. So then further, if you go down to nucleus is having proton, neutron. Then proton, neutron, further it is made up of quarks. So this is the picture, right? So this is the modern atom now. So we started with this tiny particles, and this is the picture of the modern atom now, right? So anything up to this structure? Any question? They have asked you to forcefully sit, or there is some interest? So then we have quarks, types of quarks are there. So it's just given the names up, down, strange quarks. So they are all with different quantum numbers, different masses. They have all been discovered experimentally. Right? So then the question is the whole universe made up of quarks and electrons only, or there are some more particles? So there are also neutrinos. So I'm not an expert in neutrino. There are other people sitting here, Needu and Monica, neutrino experts. So neutrinos are the most abundant matter particles in universe, and they are everywhere. But the thing is, they are not harmful, I guess, right? So every the centimeter square of Earth's surface is crossed every second by more than millions of neutrinos, but they are not harmful, right? So this is the list of elementary particles. Elementary means which cannot be broken down further. So we have 6 quarks, right? And corresponding antiquarks are there. And for the case of leptons, there are 6 leptons. So if you have an electron, you have a corresponding electron neutrino. Muon, you have a corresponding muon neutrino. So these 6 particles, 6 leptons, 6 quarks, and their corresponding antiquarks and anti-leptons. So these are the elementary particles as for today, which are fermions. Fermions, you know, they are which particles? What is the spin of fermions? Half integral, yes, that is the right thing. So the particles of ordinary matter. Okay, so this question is asked most commonly. What are we made up of? What are the basic elementary particles? If I say what is everything made up of? So the stable matter around us can be described using electrons, neutrinos, U and D quarks. These 4 particles, 2 leptons and 2 of these quarks, right? Even if there is a tau lepton or a mu lepton, I think it decays to electron and corresponding neutrino. And as a stable, as a stable particles, these 4 elementary particles are there, and we are made up of these 4 elementary particles. They exist, but for a very short time. If there is this heavier particles, they will decay into these lighter particles. So then the question is, we know these are the elementary particles, right? From theory, we know these are elementary particles, but how do we detect these particles now, right? So we detect these particles which are very, very small. You see, proton in itself is a very small particle. In proton, you go to quark, so it is very small. So to see these particles, we need very, very fine. Even if you want to see like a microscope or something, you need a very, very this with the high, what you say, magnification, right? Okay, so this is first question was what are the fundamental particles. Then the second question is how are these objects held together, right? Yeah. Okay, I will have time. So these fundamental particles. So these introduction to forces. So there are basically 4 type of forces. So these 4 forces are responsible for binding the particles together. So basically gravity, we do not take this in particle physics in the sense that it is this coupling is very, very different from this. So we can unify these 3 forces where the strong forces, they are between the quarks only. Weak forces, when we talk about weak forces, they are for this leptons and quarks. Now we know 2 categories, leptons and quarks. Then electromagnetic forces, so they are forces of this quarks, charged leptons, wherever you have this mediating particle photon. So these 3 basic forces we know. So in these forces, you see the mediating particles, they are the gluons. Like in electromagnetic, you are aware it is photon. So in strong forces, there are gluons. And in the weak forces, there are these 3 particles which are W plus W minus Z0. So these all mediating particles, they are bosons. So now as, whenever we are developing a theory, it is our, you can say, we want the things to be unified. See, if you start with this electricity, magnetism and this light radiation. So you started with electricity, you started with magnetism, but then ultimately you try to unify them. So we have this electromagnetism, right? So similarly, we want a theory which should be able to explain all the other phenomena. So our tendency as a physicist is always to develop a unified theory. So see, this electromagnetism is there. So then beta decay, where this proton neutron decays are studying neutrinos. So they come under weak interaction. So electromagnetism and weak interaction, if you unify, you get this electroweak theory. Then the strong interactions, which I told you, is to study the interaction between quarks. So this strong interaction. So now we already unified this electromagnetism weak interaction, electroweak theory. So if you unify strong interaction, the strong forces with this electroweak theory, you get standard model, right? So standard model in the present date is the unified theory for particle physics, which includes these 3 forces, right? Okay, this standard model also has some drawbacks, and people are working to get this overall complete model. So beyond standard model, people are going beyond standard model also. And I think the ultimate aim of this would be to combine the standard model and general. This is, I'm talking about future. There is no success or, for this unification of general relativity and standard model. Okay. So this is the standard model. We have quarks, leptons. Then these are the mediating particles of the forces. And also there is this missing ingredient which was proposed in the theory, Higgs boson. I will come to this, which is the Govt particle, right? So now we know these elementary things. Now the questions are, where do the particles get their mass from? Right? We know there are particles, but where are they getting the mass from? And the second most important question is, where has all the antimatter gone? So you see, at the point when universe was created, so matter and antimatter was created in equal amount. But now at present, you see there is more matter as compared to antimatter. So the question is, where has all the antimatter gone? What is dark matter? We don't know what is dark matter. And also there is a question that if we know this, there can be something else also. Like many times I have seen people talking about, we have this, or there can be many similar planets or similar galaxies, or so it is. I mean, there is a possibility there are millions and millions of galaxies. Similar kind of Big Bang might have occurred, say millions of Big Bangs might have occurred, right? So this origin of mass, it was, where do these particles have mass? So it was proposed by this Higgs. So God particle, I will discuss what this God particle does. So then this antimatter also. So experiments, they are showing, different experiments are proposed to show where this, the difference between these particles and antiparticles. Right? So this is about antimatter. Then dark matter, if you talk, so everything we see is made up of ordinary particles, but the matter forms only 4% of the universe. Remaining 96% we do not know. So this missing part is called the dark matter, and it is very, very difficult to study this or even detect this. So this is, I think, there are not all the experiments. There are many new experiments being proposed also. So these are the major high energy physics labs in the world, which are taking the data on this whatever theory is proposed. So these are very, very large, very, very big experiments, right? So I will discuss just two experiments. One is this Large Hadron, which is being proposed at this Brookhaven National Laboratory. So just to give you an idea how the things are detected or proposed to study these particles. So this Large Hadron Collider, you see, this is the ring. This is the accelerator. This and the speed which they collide is almost at the speed of the light, not c, but a little less than c. So the you can see this. I mean, the energy involved during the collision. So then there are different points where this. So this is the ring, like they are colliding here. These are accelerating here, and there are different points where they are collided. So in this, there are CMS is there, Atlas is there. So at different points, there are collision points, you can say. So where the particles collide, there are different detectors put to see what is happening. So this aim of this collider is to smash protons moving at 99.99 speed of light. Right. So these are the you can say the tunnels where these particles they are moving, and right. So then they have these points where they collide and the data is taken for that. I just wanted to show you the level of experiments. So the detectors, they are you can say these are not normal cameras. So this, you can see they are very, very large. The precision is very large. The speed with which they take the snaps is very large. It is 40 million snaps per second, right? So if you see cells, we can detect, we can see with microscope, DNA, electron microscope further. So to see them, we need these particular accelerators, these detectors. Right? So this is the fastest experiment. So trillions of protons, they travel 16.5 mile long tunnel. So they move like around 11,000 times a second around the tunnel. Right? This is the biggest detector. So it is the most complex detector ever built till now, and they can study the very smallest particle with very, very high precision. It is the coldest. You can see this large hadron collider superconducting magnets, they operate at this temperature, right? It is colder than the vacuum in the outer space even. Of this is just small part of this tunnel underground. So it is the hottest in the sense that when the protons they collide, they generate temperature which is very large, and it is almost 1 billion times hotter than the center of the sun, right? So these kind of so it takes place in a very controlled and a very precise manner, right? So particles they travel in vacuum, so it is kind of one of the emptiest, and it is the boldest in the sense that the world's most extensive computing system is being used. So supercomputers and all they are used. So just to show you the size of the points where the particles collide and the detectors, I think Iqbal, you are from So just you see the size of these detectors which are around the tunnel. There are 4 or 5 points where these detectors are. LS detector, so LHCb detector, right? So now the question is, we are trying to collide these particles at almost the speed of light. So the question most of the students ask is, or even at the time this experiment was happening, so they ask that will this large hadron collider create a new universe? Will it create Big Bang? Okay, well, news also there was many in news channels also it is saying that this world is going to end and this something like that. So this is actually misleading. So it is not, we are not creating a new universe. We are creating the conditions that existed just shortly after the Big Bang occurred, right? It is very, very energetic and all. So we are trying to create the picture of the, you can say the first sphere where these elementary particles are there. So we want to know what are the elementary particles. So you see our understanding went backwards. So from molecules, atoms, protons and all. So we just reached a point where this shortly after the Big Bang, right? So we not create a new universe. It's just that we are creating the, we want to understand the things, right? So the second experiment, which I will talk shortly, is this electron-ion collider. So which is being constructed at the Brookhaven National Laboratory for Particle Physics. So what this, there are 2 rings actually. One is in the Brookhaven lab and one is in the Jefferson lab also in US. So these facilities, they are being, I mean the infrastructure of already existing accelerators are being modified, you can say. So I will discuss what are these benefits of this electron-ion collider. So you see, this electron-ion collider will trigger this technological breakthroughs. Okay? So you see the GPS that allows you to use smartphone to lead you to a new. These are some technologies which I have listed here. So what it will do is, so earlier the detectors, we were taking the pictures, so we were not able to make a 3-dimensional picture. Your electron-ion collider will take this 3-dimensional picture from different angles it will take. So we will have a 3-dimensional picture of say proton or neutron or whatever particle we are studying, right? And then it will solve the mystery of proton spin, right? Proton spin mystery is, I will tell you very briefly. So you see, you have protons is made up of 3 quarks. So 3 quarks, they are having, I mean, every quark has a spin. So what happens is when you're talking about composite particles, so if there are elementary particles, so what should be the spin of that composite particles or charge or whatever property? You add up the 3 particles property and you should get the total quantity, whatever it is, spin or charge of that composite particle. But in the case of spin, it was it is called the proton spin crisis. Because in that case, the spin of quarks was not adding up to give the spin of proton, which is half, right? So this means that there is something else which needs to be there inside the proton, which should give the total spin to be half. So then it was proposed that, okay, there are not only quarks, but at a point of time, these quarks are further having gluons or quark-anti-quark pairs. So it happens like a quark, it creates a quark-anti-quark pair at some point of time, goes back to the quark and so on. So at some point of time, it is possible that there is a sea of quarks and antiquarks inside the proton. So it's not that only 3 particles are there, but there can be a sea of quarks and antiquarks. So this experiment will try to solve this mystery as well. Then this search for saturation. So a unique form of matter, the color quark condensate. So it may be produced in this experiment. So which will give this more level of understanding to this gluons and interactions. And also quark and gluon in confinement. Confinement is that you see, if you have a composite particle. So as I told you, quarks, they are not separate. We cannot separate them also. This is because of confinement. So quarks, they exist in a confined state only. You can have a combination of quarks, a quark antiquark or 3 quarks in a composite system, but they cannot exist individually. So this is called the confinement problem, right? So how do quarks and these questions which EIC will answer. How do quarks and gluon form the nuclei? Proton, how does it get its spin? Or how does the proton get its mass? So this is, you can see this picture, 3 quarks. So there can be a sea of quarks, right? So these are the questions for this. So as I was telling you about this images which this collider will try to create. So now at the end, coming back to the search for God particle. So I discussed this with you. We started with the Big Bang. Our understanding is going backward in time. So now the God particle. So this God particle, the name God particle came from this very popular science book by this physicist, and he wanted to name this particle as goddamn particle because the publishers did not allow him to call it goddamn particle, so it was called the God particle, right? So it has nothing, nothing religious related to it. It's not God particle. So the only God connection with this is that in the beginning God spoke and things were created of all sizes. So what this God particle is doing, it is also creating particles, or this is creating particles or giving mass to the particles, right? So this is a picture. So you have scattered particles with mass. You can relate it to, because the mathematics is very, very complex. You might not be able to understand it. So scattering of particles with scattered particles are there. There is a famous person enters the room, which is called this Higgs particle, Higgs boson. This is a massive particle. He is very famous. Now what the people do is they gather around him. So now there is a group formed, and this is how the Higgs boson or this famous person gives mass to the particles, right? So this is the last slide, and so this relevance of particle physics you can see, and you are free to ask questions. So you see, particle physics, or in general, as physicists, we do not emphasize on what is the application of this. We try to understand the things in a very precise manner, very better way. So it is up to other people who use that understanding to apply those things in other fields, right? So particle physics, so if you start with, so it's not that we are trying to understand this 3-dimensional picture, what will happen from that, right? So you know this internet? From which field do we have this internet? आज आप जो सब use करते हो internet. So it is because of which physics? No, it's particle physics. क्वांटम मैकेनिक्स तो पार्टिकल फिजिक्स में है. तो वो जो लार्ज हेड्रॉन सॉरी जो CERN में देयर वाज दिस एक्सपेरिमेंट. सो दे हैड दिस वेरी large data and there were scientists who wanted to use that data. So they had invented this www to transfer that data, which we are all using. So nobody knows this, but particle physics, even though it is a very, you can say, very elementary physics, but then applications do not come immediately. They come after few years. Quantum mechanics also, like if you are saying quantum mechanics, so everything without quantum mechanics, you do not have your gadgets. You have anything? Medical also, this MRI, lasers, everything is based on the concepts of quantum mechanics. So physics, studying physics is one thing, then applying those things is the second thing, which you cannot do without the first step.
What is your take on the current situation of our understanding of gravity in the unifying theory?
See,
does it come it under the particle?
No. It does not come under particle, because see, when you are studying when you are talking about forces, we talk about the coupling between the particles, right? Coupling means the strength with which they are, or the binding forces, if you say, no. So what is the strength? So the strength of gravity, gravity force is very different from the other three forces. So it is very difficult to unify gravity with that, right?
So can we suggest gravity as a stage to the universe, and like if we consider all the planets and the stars, they're all the actors, and there's a big play going on called the universe, and we have the gravity as the stage, and as the heavier the mass appears, more the stage goes. So I'm lacking the word. I'm sorry. Like the warping that occurs because of that in the general relativity.
See, scientists, they are trying to unify them, but at this point, I mean, there is nothing common. There has to be something common or some connection between the things, no? So in future, I'm not saying that it is not possible at all, but at present, it is not possible to unify them, but in future, it may be possible, right? So if you see the progress in the last maybe 100 or 200 years, so before 100 years, you were not knowing that we will discover quarks and we will have this picture, right? So we don't know what will be the picture in another 100 years. So nothing is impossible. But at the present, I don't think this is being taken care. People are trying. It's not that people are not trying. They are trying.
You said there is nothing common between a graviton and other forces. Graviton is a boson.
Graviton also has not been discovered. It is.
But hypothetically, we take it as boson.
Hypothetically,
so there is something common between the forces, that it is mediated by a boson.
Only this thing is there. Boson thing common is there. So every force is mediated by this boson. That is for sure. But then to unify this thing, you see. These bosons, they are of entirely different mass, and they are created at different energy, right? Gravity is, you do not need any force, external force for gravity, right? For these, to understand them, we need some external forces. So that is the thing. I can hear you, I think.
What is your take that when the scientists discovered this gold particle, he stated that the perpetual destruction and formation of the entire universe is a cosmic dance of Lord Shiva. And he even installed Nataraj in the gallery of that sun laboratory where he discovered the God particle.
It's outside the laboratory.
Yes, ma'am. So did he find something extraordinary or he didn't share that thing?
No, I think there is no direct God connection with it, and there is no connection with this Nataraj thing and the discovery of God particle, because it was there before the discovery of God particle.
That's why I'm asking you.
So
still he made this statement.
He has something to say. Might be.
अभी हम सुबह से काफी सारी फिजिक्स पढ़ ली हम लोगों ने, और बच्चों के मन में काफी सारी जिज्ञासा है। तो बच्चे ने पूछा पिछली बार भी सर के लेक्चर के बाद वाइब्रेशंस के बारे में बात की, तो वो नटराज के बारे में बात कर रहे, कॉस्मिक शावर के बारे में बात कर रहे हैं। एक्चुअली इज टॉकिंग अबाउट द फिजिक्स ऑफ कापरा, जो बहुत फेमस बुक है जिसमें उन्होंने कॉस्मिक शावर और इसके बारे में जिक्र किया है, ताओ ऑफ फिजिक्स। तो इट इज अ पैरेललिज्म बिटवीन द मॉडर्न फिजिक्स एंड ईस्टर्न मिस्टिसिज्म। So somewhat metaphysics is involved in this subject actually. तो आपने पिछले 8 लेक्चर में भी आपने पूछा मंत्रों के बारे में, recitations के बारे में, vibrations के बारे में. So obviously there is some connection between vibrations and material obviously. So whenever we characterize any material, so we apply some kind of electromagnetic field or some acoustic field or something like that. So it vibrates with its own frequency. When it matches, the resonance creates, and फिर उसके बाद हम उसकी properties पता चलती है। तो obviously इसी तरीके से हमारे साथ भी वही चीज हो रही है। हम अपने पूरी बॉडी को अगर ध्यान से समझें तो it's a bigger molecule as compared to other smaller molecules. And de Broglie theory के हिसाब से हर पार्टिकल के साथ एक वेव जुड़ी हुई है, या duality की बात करते हैं। तो obviously vibrations हमारे साथ भी हैं। सर ने बोला कि wavelength match नहीं हो रहा है, we talk about the frequency matching. So number of things are there: the vibrations, the flow of energy, the form of energy, conversion of energy. So everything is energy. So it's in the various forms that you can think about various things.
If you want, you can always connect.
Yes, obviously.
Some people they do not want to connect, but
yes.
if you want, you can connect.
It's all about the perception. आप किस तरीके से चीजों को देखते हैं। विज्ञान का मतलब ये नहीं होता कि आपने सिर्फ इक्वेशंस पढ़ ली और इक्वेशंस को आपने इम्प्लीमेंट किया, नहीं। विज्ञान का मतलब विशेष ज्ञान होता है जो आपको अपना एक फिलॉसफी आप अपनी डेवलप करते हैं। दैट इज विज्ञान, दैट इज साइंस।
But I'm very sure जब हिग्स ने वो इक्वेशन डिराइव की होगी, he had nothing like this in mind. But it is a good question, and you know what is, when a teacher says it's a good question, what does it mean? It's a really good question, or I don't know the answer. So whenever somebody says it's a good question, means I don't know the answer. So okay, thank you. And okay, there is.
I just want to add that there are many students actually I have also seen in classes and seminars who like to ask these kind of questions, philosophical questions, because they seem interesting, fancy, and also to us Indians they seem very hopeful that we can take refuge in our ancient science and everything. But in a way, it is it is also a method to escape the realism and to escape the mathematics actually, I would say. So if you really want to understand these things, I have one suggestion: please work the maths. Everything will come from there. You have to work the maths. Definitely you should be open, but then you will be left at the level of questions only, and then saying few interesting statements here and there. But if you want a deep knowledge, you have to work the maths. You have to start
Technically, you have to start technically.
Yes. So start from the mathematics.
And you can always blame entropy for whatever things you don't know.
Yeah.
But there is mathematics.
Yes. There is mathematics. Yes, there is mathematics. So work that out. No? Just like start from the most fundamental thing. Build your maths, and work out. You know, we can place our whole understanding, our endeavor is to place our whole understanding in terms of a very neat, simple equation which everyone can understand. So, but that equation may be simple, but the maths behind that would be very, very complicated, and you would need really sharp and genius minds to work that maths. So, if we're trying to work that, string theory is one way, although we have not seen any success. We have not seen any experimental success in supersymmetry. We can develop all kind of theories which needs extraordinarily sharp minds, but unless those things are experimentally discovered, they would lose their shine in few years. Okay? So if you want to already understand, not only understand, answer these questions, you have to start from the basics of science. Okay? And you have to work the mathematics.
There's one more question.
We know that graviton hasn't been discovered yet, right? It exists in theory, right? If we, let's say, tomorrow discover graviton, what would be the implication in physics? What new changes is gonna come in physics, like? What would be the revolution?
See, discovering graviton, see, theory and experimental in any, not only in particle physics, in all the things, they go hand in hand. Like sometimes you develop a theory first and discover the things later on, right? Sometimes you observe something and you say, this theory is not working for this particular observation. So there is something to add to the theory. So sometimes you work from theory to, other way, right? So discovering graviton will establish that graviton is this thing particle, but then you are talking about the unification with the other thing that is not based on the discovery of graviton. Graviton's properties, we know the properties of graviton or the quantum numbers of graviton, right? If they are discovered, that is okay. But then unification is entirely a different concept. So that is not, it is not, not occurring because we have not discovered graviton. The discovery has not stopped it, but there are other limitations for this unification. See, again, there is a lot of mathematics to it, but see, gravity, when you're talking couplings, I'm telling you, coupling constant of these quarks is very, very strong. The coupling constant is almost 1, right? For gravitons, you know what is the coupling constant? For electromagnetism, what is the coupling constant? Alpha. 1 by 137, right? For strong interactions, it is like almost 1. For gravity, what is it? Very, very small, 10 raised to power minus something. So to unify, because when you're writing an equation, so the equation you are writing a particular interaction, so there is this coupling constant coming in that equation. So when you have to combine, see, when you write something x minus y, if y is very, very small than x, what do? You leave the y term. Yeah, so it's not that just because of the coupling I'm saying you neglect that, but then there has to be some equivalence between them. Right? So all the interactions, whatever things you measure, they are directly proportional to the coupling constant. This at the back.
Ma'am, if someone wants to study quantum physics, so what's the path to take to one stage to study at higher level?
Quantum mechanics at higher level?
Quantum physics.
But quantum mechanics, you can start, you are asking me a book or what? What is the question?
The direction should one takes regarding it.
See, courses, okay, you can go through some books. There are some online lectures also on Neptel. There are some lectures are there. This is what you are asking. Acha, okay, I mean the courses or something like that. Higher education mein to see post graduation, then you can go for PhD, which related to this field. Post graduation is the basic thing. MSc in physics, right? So MSc in physics, and then you can pursue that if you want to do PhD or something. So there is lot of scope in quantum, I mean quantum mechanics, as you are saying, in future this quantum computing and other things, they will all use this concepts of quantum mechanics.
Which is your favorite subject in
High energy physics. All high energy physics, quantum mechanics. But मुझे आती कुछ नहीं है. I don't know quantum mechanics. I am trying to learn. ठीक है? But favorite वही है. I teach also quantum mechanics, quantum field theory, and it is very, very difficult to convince people because you cannot actually see the things. You have to understand it mathematically, right? But then the beauty of quantum mechanics is so much that, I mean, you cannot appreciate the world around you if you don't know quantum mechanics. It's not that it is used only in particle physics. I think material science, everywhere. Quantum mechanics in chemistry, biology, you cannot do anything without quantum mechanics. So quantum mechanics does not have application only in physics. It has applications in all the fields.
If I'm correct, then Higgs field.
Huh.
If I'm correct, then Higgs field was discovered because there were some problems with electroweak theory, right? In the Weinberg formulation of the electroweak theory.
Yeah, so when they were unifying this electroweak theory and the strong forces, so this Higgs fields was proposed at that point of time.
Yes. So if we assume that there weren't any problems at that time, then Higgs field would have been discovered. That
see, Higgs field was proposed theoretically at that point of time, but it was discovered in this experiment much later.
But the reason for finding that why particles have mass was because of electroweak theory. If there were no problems with electroweak theory, then could someone have seriously proposed asking the question why particles have mass?
No. But particles, from where do particles have mass? This is not only just from electroweak theory. See, in general, why the particles have mass? How do they get their mass? This is a very general question. But then, if you go through theory, so then it is through electroweak theory.
But then why are not people actively asking questions like, why is the charge or why is this spin?
They are asking, and people have given answers to it also. So this is, see, it's a very, very vast, very, very vast world, very, very vast area. So you cannot know everything. Whenever we are also like teaching or studying, we study a very, very narrow area, very, very narrow subject. So we can never understand all the things. But
ma'am, I want to travel with time. Is time travel possible?
You are traveling with time?
No.
Who is stopping you? You are already.
I want to go in fast.
So you can just close your eyes and go wherever you want. Nobody is stopping you. Theoretically, you can do anything.
It's meant physics fair out there.
Huh?
Physics fair out there.
Physics में? हाँ, theoretically है, experimentally नहीं है अभी तक.
I'm going to time travel.
Okay. But for that reason, that is possible. Time travel is possible, but for that you need to know Fourier transform theory. So very recently there are few papers where they are Fourier transform. Okay, so from time zone we need to go the frequency zone. Okay, so if your time zone is wide one, the frequency domain will be that Fourier transform. So the common Fourier transform, where you cannot go backward to the time, it will show you some signature. But if there is time travel, if we can go back, then the signature of the Fourier transform will be something. So some anomaly in Fourier transform we can do. Very recently, again theoretically we got that anomaly in Fourier transform. So that is a hope. But maybe we need to create some mechanism to find that way how we can get that. So people are working on that. Probably the time travel may be possible someday. But for that, first you need to know Fourier transform and other things, and need to apply that. You know E equal to mc square. We all know, but how will you apply it? Try to apply. This is a 10. You know what will be the energy if I burn it completely. If I turn it to energy completely, that is different. That is technology. So first we are working on the science using mathematics, and then we'll go for the technology. So those steps are there, and we are hoping you guys to do that. Okay, so question is good one, but we need some answers from you.
So, if you are able to do this time travel, so we would also like to do so. So keep us in mind, okay? If you are able to discover something, we would also like to go back. So keep my name in the list. I will also. You can try on me, okay? So.
Thank you so much, ma'am. Now we are going to resume our seminar with an insightful talk by Dr. Sanjeev Kumar. Dr. Sanjeev Kumar is presently working as professor in the Department of Physical Sciences, ISIR Mohali. His research area focuses on theoretical and computational study of strongly interacting and disordered electron systems. He is presently working on topological magnetic texture in spin orbit coupled system, ordering in low dimensional frustrated quantum magnet. He has published more than 60 research articles, some of which include anti-ferromagnetic skyrmion crystal on triangular lattice, and many more. Sir, we are pleased to have you here. Please give him a big round of applause.
Thank you so much. Am I audible at the back?
Yes.
All right, great. Okay, firstly, I would like to thank the organizers to invite me to present here. I unfortunately I could not join in the morning session. I would have loved to. Nevertheless, I had some interaction with students who are posters, and it was a very nice experience. So I am going to talk about today about sort of a general idea that we worry about in condensed matter physics. So I'm essentially trying to give you a flavor of what condensed matter physics is all about. I think in the morning you heard one talk about particle physics, and therefore I would try to argue that in condensed matter one also worries about particles, but of a different nature, and I'll give you examples of those. So this is the plan for the talk, and roughly it is, you can think of this in two parts. Part one is I'm going to give you various examples of the idea of generalization of the idea of particle. Okay, so when we say particle, we have to really, as a physicist, ask how do I actually define a particle, and this question leads to a very general concept. Okay, so what is a layman's idea of a particle is very different from what is a physicist's idea of a particle, and this distinction has to be clear to begin with. And once you understand that this distinction is there, you would appreciate many more phenomena in nature in a different way. I'll discuss some examples of this in classical and quantum physics. And finally, part two of my talk is going to give a little bit of flavor of my own research work, which is on magnetic skyrmions. So I'll discuss some ideas, and in the process, I'll also introduce you to those students who are interested the concept of Monte Carlo simulations, which is a very interesting tool to arrive at theoretical results on complicated systems. Okay, so let's begin with, if I pose this question of what is the definition of a particle. Actually, it's a very you realize that it's not an easy question to address. And when you think about it, the definition of a particle, why is it difficult? It is difficult because we actually don't have systems of isolated particles so easily available to us. If you look around in this room, can you give me an example where you can say that sort of that here I have isolated particle? Typically, what we encounter in the day-to-day life is a collection of particles. It's a system which has many particles. And out of this now, I have to worry about what is actually the particle. Okay. So how do we go about defining a particle? The physicist's definition of a particle would be that I would take a system, because mostly what is commonly available to me is a system. And on that system, for example, this screen is a system. If I ask what are the particles there, the approach to answer this question would be that I'll do some experiment where I'll disturb that system by imparting certain energy and momenta to that system, and then observe what is the response of the system. So depending on what are the particles in that system, the response would be different. And this is how you would identify what are the particles making up that system. So if you think of a simple example, let's take ideal gas. In ideal gas, if I ask what are the particles, this question becomes dependent on certain things. This becomes dependent on what is the energy that I'm imparting to this system, right? So if I give a gentle low energy to a system of collection of gaseous particles, I would see the individual molecules of the gas moving around. So the energy and momenta would be taken away by those individual particles. So at that energy scale, my system is made up of molecules. I increase my energy count a little bit. I push that system with a heavier energy, higher energy. Those molecules can dissociate into atoms. That's the next process. And if you probe at that level, then you would say that, okay, my system is actually made up of atoms. You can keep increasing your energies further. If you go to the next level, you increase the energy further, you would say that, okay, atom can be now broken up, the electrons can be pulled out from the atom, you're ionizing the atom now. And now the system is made up of electrons and ions. It's a collection of electrons and ions. And then you keep on going further and further, and at very high energies you would actually break open the nucleus, nucleons will come out, and then you say the system is made up of nucleons. So the question, what is the system made up of, depends on at what energy you are probing it. Okay? And if you think about it, in high energy physics, the holy grail is to figure out what is that final particle. If I keep going to higher and higher energies, is there some scale at which I'll stop and say these are the most fundamental particles in the nature, and everything is just now collection of these? This is the question that high energy physicists worry about. Condensed matter physicists worry about a different question. Condensed matter physicists worry about a question which is what happens at low energy scales. What we see today, the natural disturbances of a system come from temperatures, for example. You have slightly hotter system, then the particles in that system will start doing something, and so on. So condensed matter physics worries about the definition of particles in a system at low energy scales. So that's why condensed matter is also known as low energy physics. And one would realize that in order to understand certain phenomena, you will have to worry more about the low energy physics rather than high energy physics, right? For example, water makes a surface wet. This is an example of a phenomena, right? If you know what the most fundamental particle in the nature is, which is some, let's say quarks, gluons, and so all that, would you be able to explain this phenomena that water wets the surface? The answer is no. So at every scale of these collections of particles, there are going to be new phenomena that will appear, and understanding of that phenomena depends on understanding the low energy particles in the system. It will not depend on the most fundamental particle. So if one day energy physics actually figures out that the most fundamental particle is X, Y, and Z, it does not mean that we can stop doing physics, right? So physics is very at every, and we have to address these questions at that level itself. Okay? So this is the idea that I'm going to sort of present to you. And so next I'm going to show you an example. This movie is running right on the left. Here is a very common example of what one kind of means by a collective particle. So this is a bird flock that you are seeing on the screen, right? So you can see that these small birds, collection of them, actually behaves like a bigger object. And if you see that they actually sometimes chase away the bigger birds by becoming larger too. So if you look at this phenomena, it seems that the effective particle is this bigger bunch. Although it is made up of very small particles, but at certain scales, you are actually able to see only the bigger object. Another example, which I should be able to play somehow. Yeah. So this is what is known as a fish school, and this is also a common example. You might have seen these things on Discovery Channel, for example, that these smaller fishes, the smaller fishes actually behave together as a bigger animal. So, so these are actually known as sardines, these fishes, and the bigger fish is tuna, which is trying to approach. So tuna individually tries to eat this small fish, but these small fishes take up the shape of a bigger object, and it can actually chase away the bigger fish or scare away the bigger fish. So these are examples from classical physics, which can roughly tell us what I'm going to talk about, which is collective objects, collective phenomena, collective objects. Now let me come to the examples. So this is a simple model which can explain such phenomena, known as a Wischek model. And here the model is simply you take individual line-like objects and they are moving according to the simple law that the direction of motion of a given particle is like the average of the direction of motion of the neighborhood. So if you apply this simple principle and solve some classical mechanics problems, we'll not go into details of this, then you would find out, let's see, this movie should run, yeah. You would be able to find out that at higher densities, you would be able to see the clustering. Movie is somehow stopping in between. I don't know why, but okay, so it should sort of go on, and you will see that in the right hand side there should be a clustering of these objects, much like the fish school and bird flocks, and therefore the phenomena that we saw in nature can be actually modeled with very simple model, which is known as Wischek model. Okay, so this is classical physics. Now let's go to the general idea of condensed matter physics. And here I have made a list for you, which is you identify a building block and then you worry about what are the different phases that can be made up from that building block. So the simplest example is sitting in the first row, which we all know about. If the building block is that of atoms, if my constituent particles are atoms, then I can make up a regular solid of these atoms. I can make up a regular liquid of these atoms, and I can also make up a simple regular gas. So these are normal solid, liquid, gas phases. When we talk about solid, liquid, and gas phases, we talk about normal atoms as being the constituents of those phases. If I take electrons as my building blocks, then we have some phases known as Wigner crystal, which is a pattern in which the electronic charge can localize and make a crystal of certain kind. That's known as Wigner crystal. It is a well-known phase. We all know about Fermi liquids. These are basically liquid-like collection of electrons. So now, when we are talking about Wigner crystal, Fermi liquid, or the some famous Sommerfeld gas, which you might have studied in your BSc and MSc courses, these are examples of phases which are coming from the electrons being as building blocks. Okay, and now you can actually go on and extending this list further. So you can have phonons. Phonons are nothing but essentially quantization or normal modes of vibration in a lattice. And when you think of those guys as particles, you can construct the phases which are equivalent of the solid, liquid, and gas. And you would see that somewhere there are dashed lines, which means that these have not been realized in nature. So there are certain possible phases in this which have not been realized yet in nature. Phononic crystals are well known. They have many applications. Phonon gas is what we encounter when we try to study, for example, the simple model of heat capacity in solids, and so on. But the liquid phase of phonons there is no such known example that exists. So it would be interesting to actually figure out what this is. Similarly, if I take spins as the building blocks, then ferromagnets or other kind of ordered magnets are my equivalent of solids. They are the analogous of solids. Spin liquid phases, something known as also known as a correlated paramagnet, a spin liquid phase, that is the analog of a liquid. And paramagnets, which are also very well known, if you take your magnets and raise the temperature, then you go from a ordered magnetic phase to a paramagnetic phase. and these paramagnets are also very well known. So these are all known examples. Spin liquids, there are some hints that such materials exist, but they have not been confirmed yet. So this is sort of in between being a name and a dash. Similarly, I can think of Cooper pairs as the building blocks. If I think of Cooper pairs as building blocks, then my superconductor, or similarly bosons as building blocks, then the superconductor or superfluid is the equivalent of the solid. And again, a Bose liquid is missing. A Bose liquid or a liquid made up of Cooper pairs is a phase that is missing. If somebody can discover that phase, that will be a great news. Bose gas is well known. So you take these either the Cooper pairs or any other bosonic system, and you heat it up at take it to higher temperatures, and you would find a Bose gas. So this list is not exhaustive. You can actually keep taking different building blocks, and you would keep realizing different phases. And this is a general theme of condensed matter physics, that what you call a particle depends on what is the system at hand, and in different situations, something else is relevant as a particle. Okay. So when you talk about solid state physics or condensed matter physics, typical view is we have atoms, they combine and they make solids. They can be in the liquid form and they can be in the gaseous form. But this concept can be generalized to any other constituent particle. Okay. And this is a part. This is a point that is important to realize and appreciate. Okay. Now let me give you a textbook example of an emergent particle, and this essentially goes in parallel with what we study in our first course in solid state physics as the theory of heat capacity. So it is well known. It is an experimentally observed fact that the heat capacity at low temperatures of solids, of most solids, insulating solids with no magnetism and so on, it behaves as cubic power of T. The specific heat, if you plot as a function of T, it will grow as a cube of temperature, T to the power 3. What happens if you try to understand this? So understanding means that we have to actually come up with certain models, and then further do the calculation, and then at the end of the day we'll end up with a certain temperature dependence of the heat capacity. If I take my model as a simple classical collection of particles, so I say that okay, solid means I have a collection of atoms, and imagine these atoms being as independent particles, then the answer that I get for heat capacity that it should not depend on temperature at all. You just count the degrees of freedom, and you would get what is known as a Dulong-Petit law, which is 3 kb for each degree, each particle. Okay. So no temperature dependence is what you get as an answer, which means the heat capacity should be just a flat curve down to low temperatures. Einstein showed that can be improved if you treat these particles as quantum mechanical particles. So in this first example, you treat these atoms as simple isolated harmonic oscillators, but classical ones. In the second case, in the Einstein's model, you treat these particles as quantum harmonic oscillators. Once you treat them as quantum harmonic oscillators, already you fix this issue with no dependence on T, but now you get an exponential dependence on T. So you have some dependence on T, and this is heat capacity is also going to 0 at low temperatures. That is all good, but you have an exponential dependence, and it is not like T cube. Now this is where Debye actually came up with this interesting idea that atoms are not independent harmonic oscillators. They are connected to each other. Therefore, it is also a way of supplying energy to the system. Right? So when you are trying to heat up a system, the question you are asking is, what are the particles that are taking up this heat? In the first two models, we are assuming that it is an isolated harmonic oscillator, either quantum or classical, that is taking away this heat. In Debye's idea, you say that no, those are the wrong assumptions. The particles are not the independent atoms. Particles are actually to come from the collective excitations of this. And this on the right, I have drawn this normal modes of oscillations for a given collection of some n particles. So you see, these are the low energy excitations of the system, and the what you call particles are going to be the quantized versions of these classical oscillations, and this is what we call phonons. Solid, one doesn't think about atoms vibrating, but one thinks about phonons being excited. So you just create more and more phonons. When you apply this idea, immediately your T cube law comes up. So this is in some sense a textbook example of what one calls an emergent particle, that although the system was made up of atoms, but here comes something else, which we call phonon. It is an outcome of the fact that those atoms were actually talking to each other. They were not independent, and therefore the disturbance of the system by some means, either heat or something else, will not excite an individual atom. It will excite all the atoms in a collective manner, and this collective excitation is actually a phonon. Okay. Now let me give you more. So this is a textbook example, but let me give you more examples of this. Before that, you can, again, it's all textbook physics, and I think people who are in MSc, they might already know about it. Students who are in BSc, for them maybe something new here. So one question is, why is it that electrons in solids actually behave like free particles? And this has to do with the very well-known theorem in quantum mechanics known as Bloch's theorem, that if you put a particle in a periodic potential, then it will have certain similarities with the eigenfunctions of this system, this Hamiltonian, will have some similarities with the plane waves. And this is where the electrons in solids in any periodic potential will have some features which are common with free particles. In some sense, the way it comes about is that typically, if you draw the energy versus momentum relation for the for particle in a periodic lattice, you will get some kind of cosine functions mostly. And this cosine function at low k, at low momenta, is going to give you, you do the Taylor expansion, it is going to give you a k square. And it is this k square which is a free particle-like behavior. Because free particle is h bar square k square by 2m. In solids, in periodic potentials, you typically get a cosine k, and this cosine k is giving you the free particle-like behavior in the low momentum range. But what is interesting is that this is dependent on what kind of periodic potential you have. And this has led to many interesting things. For example, Dirac fermions in graphene. Okay? So it turns out that if this electron, instead of living on some square lattice-like potential background, if it is living on a honeycomb lattice, if your background structure is that of a honeycomb, then the dispersion will turn out to be linear in momentum. The leading term in the dispersion at certain k points will not be quadratic. So you will not have a cosine term. Instead, some sine term develops, and the low k expansion of the sine term is going to give you a linear in k dispersion. And the linear dispersion in momentum is exactly what one expects for Dirac fermions, right? So this, of course, has its own story of how, what I've shown here is a picture. This is the material for a Nobel Prize. Can you believe it? A pencil and a sticky tape is a material that led to a Nobel Prize. It's just about how how original you can think. So graphene is nothing but a single layer of graphite. So all you need to do is somehow pull out that single layer of graphite. Graphite, as you know, it is easily cleavable. It's very easy. The interlayer connectivities are very, very weak. So the layer itself is very strong, but the interlayer connectivities are very weak. So these scientists, Rime and Novosilo, these guys actually figured out that the easiest way is I put a tape. So they sort of took a graphite pencil, covered some paper with it, which means you have actually graphite layers on this paper. Then you take a scotch tape and it's trial and error. Keep pulling off these layers from this pencil shade on the paper, and actually sometimes if you're lucky, you get actually a single layer, which means it's just a one atom thick layer. You have just pulled off a single layer of that honeycomb structure, and that has many remarkable properties. So this is, of course, this has led to a whole industry in some sense, because you realize that graphene is a very strong material if you think in terms of the standard definitions of strength and so on, and it is replacing many of our standard sort of materials now. The engineering aspects are coming in. You can make graphene nanotubes and so on. So by the way, this guy Gaim is probably the only guy who has a Nobel and Ig Nobel. And does anyone know from the students what did he get this Ig Nobel for? Anybody knows what did Gaim get his Ig Nobel Prize for? It was there on one of the posters. That's a hint. This picture was there on one of the posters. So he is the same guy who levitated a frog on a superconductor, showing that frog has some magnetism inside it, and if you put it on top of a strong superconductor, frog will not fall down. So he just showed a frog, live frog, hanging in air. So he got an Ig Nobel Prize for that, because that's a very interesting phenomenon, but it has a funny aspect to it. That's what the Ig Nobel Prize is given for. Right? So yeah, only guy with some of these unusual ideas. So what is he thinking? I don't know. He's thinking about putting frogs on superconductors and taking a pencil and a scotch tape and pulling off a single layer. Okay, so very interesting guy actually. Okay, good. So this is as an example, what I was discussing is a idea of an emergent particle. And here you have, in a condensed matter system, you have a particle which you typically worry about in high energy physics, Dirac fermion, right? Usually you have this particle in the relativistic sort of limits. Okay, but here you have a Dirac fermion. The dispersion is of this kind, a linear, and in the high energy physics, it would be the speed of light here. But here your Fermi velocity is 300 times smaller than the speed of light. Okay, let's go on and some more examples. Majorana fermions. So if you take a superconductor has a potential to generate many unusual excitations. So what is the typical, okay, but what is the understanding of a superconductor? It's a very unusual phase, and it's something that is not so nicely covered in textbooks. So the main idea of a superconductor is that if you supply energy into, so we are thinking in terms of the general picture, right? I take any system and I supply some energy to this system and ask what are the excitations in that system, right? We did that for the phonons when I took a solid, supplied energy to the solid, and we found out that the excitations are phonons, the collective modes of oscillation of these atoms. So if now I take a superconductor and supply energy to the superconductor, what is it that gets excited? Is it electrons that get excited, or is something else? Answer is, the excitations in a superconductor are what are known as Bogoliubov particles. And a Bogoliubov particle is a superposition of a presence and absence of an electron. It's a very weird thing. It's a superposition of an electron and a hole in some sense. Okay, it comes with different coefficients and so on. Now, typically in the conventional, what is known as conventional superconductor, you would have a superposition of this type, that an electron with spin up and a hole with spin down is what is kind of linearly combined. It's a linear superposition of two states. One state is electron with spin up, the other state is a hole with spin down. This is what happens in the standard, what is known as singlet superconductors, up and down spins. The typical picture for Cooper pair is also made based on this, which is just up and down electrons with momenta k and minus k pair up. If you look at certain unconventional superconductors, some of which are actually being claimed to be discovered, but there is still research going on, there you can have actually electron and hole pair both having same spin. So you can have an electron with spin up and a hole with spin up having a linear combination. So that the excitation of this kind of a particle is an electron and a hole with same spin orientation. Now, if I take the conjugation of that, under conjugation, the electron becomes hole and hole becomes electron. So if I take conjugation of U times E up and V times H up, I get U times H up and V times E up. Now, if it also so happens that the coefficients U and V are equal, then this kind of particle will represent a Majorana, because the particle comes back to itself after conjugation. So the particle is its own antiparticle. So this is a very, very important topic of research currently, search for Majorana fermions in superconductors. And the first step for this is to really identify these unconventional superconductors where you can have the excitations as the linear combination of electrons and holes with the same spin orientation. Okay, once we discover that, we are actually all set for discovering Majorana fermions. This is well known. So this is a highly interesting research topic in condensed matter physics today. Okay, let's see what are the other examples. Right. So coming to, I'm sort of now trying to come to the second part of my talk, which is going to be about magnetism. And to lead to that, one can ask, why in what situation does the spin become a effective particle? So imagine you have a lattice, and on this lattice, which is a collection of atoms, each point represents like one atom, and on this lattice we have as many electrons as the number of sites. And these electrons are repelling each other very strongly, right? Electrons repel each other with the Coulomb repulsions. So you would realize that every electron would want to just occupy at one individual site, and it would get frozen there, because anytime this electron wants to move to the neighboring site, you will have actually two electrons coming closer, and that will have a very high repulsive cost. So in this situation where the interaction energy is large for these electrons, you would obtain a state where all electrons are happy sitting in their own locations. Now again, I ask about or think about the same experiment. Let's impart energy to this system. What would it do? If the interactions were not small, if the interactions or the repulsive interaction between the electrons were not large, then after imparting the energy, these electrons themselves would move around. Now this process is stopped because there is a very strong repulsion between electrons as a charge repulsion. So the electrons will not be able to move around. But does it mean that this system will not be able to absorb any energy? Will its specific heat remain zero up to some temperatures? The answer is no, because electron actually comes with 2 degrees of freedom. It has a charge and it has a spin. Although due to the Coulomb interactions, the charge degree of freedom has been frozen, that has been put into place. The spin degree of freedom, which is the freedom that the electron has to do this up and down motion, that is still active. So if you impart energy to this system, such a system, the spin can still can absorb this energy. So you can have spin flips, and actually, if once again it is the same situation as that of atoms, a single spin will not take the energy because these spins are connected to each other. The energy will be taken as a collective excitation of these spins, and this collective excitation of spins is what is known as a magnon. So a magnon is like normal mode coming from the spin orientations, not from the oscillations of atoms themselves. So phonons are atoms themselves tied on a rope in some sense. This rope is oscillating. That's your phonon. The magnon is that there are spins on this line, and these spins are flipping, and they are flipping in certain pattern. Okay, they are generating a wave-like pattern of flip. That's your magnon. So this is the situation in which spin becomes the effective particle. Spin becomes the effective low energy particle. So all your magnetic materials are typically belong to this class, where the main degree of freedom in the system, main particle in the system that you are worrying about is the spin degree of freedom. Okay, and then one worries about how these spins talk to each other and so on. Okay, so yeah, so this is essentially part 1 is what I meant it to be. It's sort of done. Now I'll just, in the remaining time, how much time do I have? Can I take like 15 minutes? Yeah, I think that is comfortable. Okay, so now now I'll mostly discuss the idea of magnetism and magnetic states. So if I have suppose I have a situation where the charge degree of freedom is frozen. Now I'm left with only the spin degree of freedom, and I can ask the question, now what are the main phases possible in the system? So you still have many possibilities for phases, and I can broadly classify them in 3 categories. One is what I call collinear phases. In a collinear phase, the spin orientations will be in a line, up or down. So there are only 2 possibilities. The spins will be either up or down, and at every lattice site, I can have either up or down. That can lead to still various phases like a ferromagnet, antiferromagnet, and a ferrimagnet. There is second class of phases which is non-collinear. Non-collinear phases, but coplanar, which means that these spins can actually traverse a plane. They can continuously change as you go from side to side. The spin vector can orient in a continuous fashion. It need not be just doing up and down, but this remains in a plane. The whole structure remains in a plane, which means if I orient myself in the right direction, all the spins are lying in one plane. That's a coplanar structure, but non-collinear. So collinear, non-collinear but coplanar, And the third most complicated one is non-coplanar, which means all three directions in space are utilized for these spin orientations, for the spin patterns. And this is the picture here, where this band color, the yellow and red like thing, that is representing the z component of the spin, and the x and y components of spins are shown in the plane of the screen. And therefore you realize that this is actually a non-coplanar spin state. So all these states, all these types of states are possible in condensed matter systems. And in particular, what I'm going to just tell you briefly about is this idea of a skyrmion as an interesting particle. Maybe it's fine now. Yeah. Am I audible at the back? Okay. So so what I'm going to talk about is this certain specific type of a non-coplanar pattern, which is known as skyrmion. And as I've shown here, this is what a skyrmion looks like. So let me sort of explain it in simple words. So look at the central spin here. The central spin is pointing down, and then you move out radially from that central spin. As you move out radially, at every value of the radius, the spins actually symmetrically start tilting from down to up in a symmetric way. Okay? So the spins start tilting down to up, and eventually at some radius, everything becomes down. So if you go out there, that's just a ferromagnet with all spins pointing up. And this object here, which is having one spin pointing down, and then neighborhood of that spin having slowly tilting upwards, this object is known as a skyrmion. And this comes in two varieties. One is Neal skyrmion. In the Neal skyrmion, as you go outwards from the center, the spins point radially outwards. You have also a block skyrmion, where the spins don't point radially outwards. They start pointing. They start having a component along the tangential direction as well. So they still swirl upwards, but the process of swirling is not going from this to this, but it's from going from this to this. So it sort of has a tangential component before going upwards. So these are the two classifications of skyrmions. And well, there is a sort of mathematical definition of what kind of a configuration of spins would be a skyrmion. In fact, it is a very interesting sort of thing in topology or geometry, that you can define topological charge, which is some integral of the spin orientation. So that's not really important for you to worry about right now. If you're interested, you can look up this formula later and try to figure out yourself why this quantity is sort of a charge like conserved quantity for these objects. The main idea about these skyrmions is that they are very stable objects. They have a certain pattern to this configuration, which is not very easy to unwind. So it's like a knot in your spin configuration. Small size particles, which can be utilized for many purposes. And in fact, there are proposals of using what is known as a racetrack memory device, or building a racetrack memory device based on skyrmions. This essentially involves, so these skyrmions can be also made mobile in the system. They can be with tiny applied currents. You can make these skyrmions run along a track, and on that track you can have ways of a magnetic system subsystem interacting with those skyrmions, and defining a bit. You can have a read head and write head, and as the skyrmion crosses these heads, some information can be sort of stored. So this is actually believed to be one possibility for a next generation computer technologies. Okay? If you can have really stable skyrmions which can be run in a really straight line, then you can actually make is what is known as racetrack memory devices. So this is another topic on which the research is really actively going on all over the world. Okay, good. So how do we in fact observe this skyrmion? So you realize that what we are talking about. This, if I want to see this in a real magnet, you notice that in a real system, the spacing between two atoms is typically a few angstroms, right? So I need a really precise camera to take a picture which shows me the spins as vectors pointing, right? And well, so do we have such a camera? Well, so this is what it is. spin polarized scanning tunneling microscope, a spin polarized STM, is what is giving you this kind of a camera which takes a picture of the system and maps out the spin configuration for you at that scale. Okay. So this is, for example, in this example is shown here for a system which has iron and iridium, some interlayers, and one can show by this STM images that this is the pattern of spins. So this green arrows and red arrows, they are the orientation of spins. Essentially, the principle on which the STM works is that it tries to measure the tunneling current, and the tunneling current from the tip to the sample depends on what is the orientation of the spin in the sample. And then you can back calculate, you can write a model and back calculate and map the spin configuration of the underlying system. Right? So there are experimental techniques available to really look at these configurations of spins at that scale, and that is why we are confident that such systems exist. So this is known as a lattice of skyrmions. So think of this as the skyrmions are packing nicely as a lattice. Okay, so now this is where this is little bit of sort of theoretical approach to the problem of how do we identify in a given material what kind of magnetic state is present, right? And that basically depends on what is the Hamiltonian of that material for the spin degree of freedom. Now, typically the Hamiltonians come in different varieties. So just to give you examples, if I have a Hamiltonian which is like this, it is exchange interaction J and the dot product of two neighboring spins on a line. Now, if this J is negative, if J happens to be negative, then it doesn't take much for us to guess that the magnetic configuration for the system, which will be lowest in energy, would be all spins pointing in the same direction, because that will give the dot product 1 and J is negative, so that's the lowest possible energy you can get. Now let's look at this Hamiltonian. This Hamiltonian has two terms, normal dot product like term, right? Exchange coupling, and this is known as Zalesky-Moria coupling. This is a coupling that originates from relativistic effects in systems, and in some systems this can be significant. And so look at the nature of this coupling. It is some constant vector d vector dot Si cross Sj. So on the nearest neighbors, it is the cross product of the two spins that matters. So if you look at the competition of these two terms, you would find that the spins that would give you the best possible energy, the lowest possible energy, are going to be the these non-collinear phases where the spins are tilting around. So you can explain collinear phases with the help of this term. You can explain non-collinear phases with the help of this term. So given the material, you would have to figure out what are the relevant interactions there. Is it only J that matters? Is it J plus D that matters? And so on. So this is a question that would become dependent on the material that is at hand. And one has to do that background study and figure out which Hamiltonian describes my magnetic system. And that Hamiltonian then is, but given a Hamiltonian, this is still not so easy. So these two examples that I had shown were actually the easy examples where you can just look at the Hamiltonian and figure out what the state would be which has the lowest energy. In general, this is not a very it's not a very easy task. So for example, if I take the most general Hamiltonian with all components of spins coupling with each other, you would not be able to figure out so easily on a lattice as to what is the lowest energy state. Another example is what is known as frustrated magnets. So imagine your lattice being triangular and your interaction being positive, J is positive. So every pair of spins now wants to be anti-parallel. But if I decide this pair to become anti-parallel, the third spin here does not know whether it wants to be, it has no preference. It cannot be anti-parallel to both. So this is known as a geometric frustration, and there are many magnetic materials which are known as geometrically frustrated magnetic materials. And typically these materials give rise to very interesting ground states which are not so easy to figure out. Okay, so what I am trying to motivate here is what is the most general way to address this question that given a Hamiltonian, how do I find out which magnetic configuration will give me the lowest energy? And one of the methods which is very successful in doing this is what is known as Monte Carlo simulations. So Monte Carlo simulation, when you talk about Monte Carlo, one typical example which I think many of you know is that you have random numbers giving you information, right? So you can, this is a very simple exercise that many of you might have done, how to calculate the area of a circle using random numbers. So, but in statistical mechanics, how do we use these random numbers and how do we use Monte Carlo simulations? So here the idea is that the quantity that you're interested in is partition function. So you have to somehow get to the partition function. And partition function simply depends on the Hamiltonian, of course. So it is, as it is written here, this is your, if mu denotes a certain state, then that state will have a certain energy E mu, and the probability of that state occurring is given by this factor. So if I want to calculate any quantity in a statistical mechanics system, I would have to worry about calculating that quantity for a given configuration, multiplying by the probability of that configuration to occur, and go over all the configurations, and then finally my answer would be there. Trouble is that this process, if I want to do it rigorously, is a very complicated process. And as an example, if I want to take a system, an Ising spin system, which is just a system with spins having up or down, which means at every state, every site, I have just two spins. I have just two configurations, up or down. And if I take 25 such sites, the total number of configurations is 2 to the power 25. So I have to one by one go to all the 2 to the power 25 configurations, calculate its probability of occurrence, which is e to the power minus beta E mu, and calculate whatever quantity I am interested in for each configuration and average it out. This is a very, very heavy process, and there is no way you can solve problems like this. So the way out was a very clever idea, which was known as importance sampling, and related to it is Metropolis algorithm. I'll not give you the details here. You can, of course, these are just, I mean, this talk is just meant to motivate you to learn these things later on, and there is no way you can learn all of this in 1 hour. But the key idea is that let us not even visit those configurations which are not important. What do I mean by not important? If the probability of a given configuration is very small, then I wouldn't worry about calculating the value of the quantity in that configuration. If you apply this idea, this is the idea that is applied via this Metropolis algorithm, then your calculation will become very simple. And instead of worrying about 2 to the power 25 configurations, you can worry about just 10,000 configurations and get your answers. Because it turns out that it's only very small fraction of configurations are actually important in a given system. Okay. So those who are interested in computations and so on, I encourage you to look at this algorithm. How good are these Monte Carlo simulations? Well, so in order to test any method, what you should do is you should basically look at the look at an example where exact result is known to us, and then apply your method to that example and ask how well does it do. Now here, this is exactly what we do. So you take a two-dimensional Ising model, which is exactly solvable, and these two graphs are showing the magnetization versus temperature and the specific heat versus temperature for the Ising model in 2 dimensions. The black lines are exact results. Those are analytically derived exact results. And the red dots are results obtained from Monte Carlo simulations. So if you can do this simulation well enough, these results that you obtain are essentially exact. Okay, that's the power of this method. Okay, so now finally I'll just discuss the Hamiltonian that we have studied recently in relation to the skyrmion formation. And this Hamiltonian has this character. Now this Hamiltonian, well, it has been derived from a more elementary setup where you have to worry about electrons interacting with each other and electrons hopping from side to side. So once again, I don't have enough time to get into the details of how this is derived, and also it is a bit involved. It's technically quite involved. But basically, there are 3 terms here. One is a dot product term, Si dot Sj, which we discussed. Other is the Zelsinski-Moria-like term. So there is a D vector dot Si cross Sj structure to it. And there are third terms which are dipolar-like. So when you look at dipole-dipole interactions, there is a m dot x cap into m1 dot x cap into m2 dot y cap and some stuff like that. Right? So the third term is of dipolar type. So this Hamiltonian consists of these terms, and this is where what I discussed about Monte Carlo is useful. If I was given this Hamiltonian and we had no idea about Monte Carlo simulations, there'll be no way I can actually tell you what are the best configurations for such a Hamiltonian. This is as complicated a Hamiltonian as it can get for the spin systems. So this is what we see now. Unfortunately, the two movies that I had here are not working, but hopefully this slide will cover for them. So what we have basically obtained is that the spin configurations for this Hamiltonian look like this. So you have these domain walls which are randomly orienting. You can have, under different circumstances, you can have a collinear like magnetic pattern, and more interestingly, you can have this crystal of skyrmions. So this is, if I compare this picture with what we saw in the experiments on iron iridium, it's almost exactly the same. So, and the Hamiltonian that we have derived is actually valid for iron iridium like systems. So there is a connection of why it should be like that. So we are able to show that using Monte Carlo simulations, you can obtain configurations of spins which are the best energy configurations for that given Hamiltonian, and they actually they actually have states which are skyrmion crystals as well. If I had those two movies, you would have appreciated it slightly better. Unfortunately, that is not working out. So this brings me to the summary of this talk. So essentially, as I said, two parts. So in the part one, I tried to motivate to you the idea of how one should think about a particle as a very general concept, and what is a particle depends on the question as to what energy you are probing your system. So a system is made up of particles, but this question, what is the system made up of, is dependent on to what energy you are probing your system. And so the question in high energy physics is, what is the final small particle or collection of particles which the matter is made up of? But the question in condensed matter physics is, if you want to understand a specific phenomena that we observe in the lab, which particles would explain it? This is a reverse question. Okay? So then I discussed some specifics of our recent study where we talked about, where we have studied this presence of skyrmions in a magnetic system. And well, this image is also there. So these are also some of the configurations that we obtained from our study. The right hand picture is an experimental data where we see in the experiments, through these STM like experiments, we see, one sees, I mean not we, these are experimentalists from Japan who have reported the presence of these filamentary domains. These are known as filamentary domains because they sort of run around like filaments. And as you apply magnetic field, they become a collection of skyrmions. These objects are skyrmions. In the theoretical study that we have undertaken, we find at zero magnetic field, the filamentary domains are present, and as you apply magnetic field, these filamentary domains actually turn into isolated skyrmions. So I think with that, I would like to thank you for your attention, and sorry for the delay. Questions? Yeah. Right. 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 So it's like so let's ask the same question about phonons. So phonons किससे बने हैं? Those particles are actually sort of collective excitation of the system. So phonons are not made up of something more fundamental. They are actually realization of the atoms themselves under some circumstance. So just like phonons are not made up of anything fundamental, they are just excitation, collective excitations. Those Bogolivo particles in superconductors are collective excitations of the electrons and holes. That's so there is no fundamental high energy particle that is making them up. Right? Yeah. Non-coplanar magnets. So firstly, as a fundamental state, it is very interesting. Typically, you expect that magnetic systems would go into either collinear states or coplanar states. So non-coplanar systems have other applications like if you have a metallic system where the background is non-coplanar, then you would have many, you would observe many phenomena which would be as if there is a magnetic field present in the system. So if an electron travels around in a system which has a non-coplanar magnetic background, then this electron will gain certain phases. And these phases are going to be similar to the phases that electron gains when it travels around in a magnetic field. So the non-coplanar magnets actually generate intrinsic magnetic fields for the system, which can have many interesting applications.
Any question?
When you explain, so when you explain the Majorana fermions and the B.Voc fermions, you wrote an equation which explains
E plus this thing, right? Yeah.
Right. The last equation that which is the condition for Majorana fermion.
Right.
And if U is equal to V, then then the particle with its own entity.
Yes,
Can
exactly.
you explain the logic behind that?
No, so if suppose U is equal to V, then you are taking conjugation of this, right? Under conjugation, electron goes to hole and hole goes to electron. But then the end result here, U times H up plus V times E up, is same as what you started with before the conjugation, because U is same as V. So you started with something and you did conjugation, you got the same thing back. Typically, if I have an electron and I do conjugation of electron, I get a hole. When I did conjugation, I got a different particle, which is the antiparticle of the starting particle. But if I have a linear combination of, suppose you forget the spin for the moment, suppose you had just E plus H. If I have E plus H and I take conjugation of it, I get H plus E. E plus H is same as H plus E. Therefore, this is the antiparticle of its own.
That means it's an antiparticle.
No, antiparticle you would get, so hole is an antiparticle of electron. But in this case, with this linear combination, whatever you started with, after conjugation also same thing appears, which means the particle is its own antiparticle. Right?
So it means hole and positron are same.
Yeah, so yeah, hole is in condensed matter systems, mostly hole is used because the band inversion is there and so on, right? So absence of an electron is a hole in condensed matter systems. Positron is more like a fundamental high energy particle. So while they have some similarities, they would not, I wouldn't call them exactly same. So hole can appear with, see, in condensed matter, electrons can appear with different masses in the sense that it depends on the band structure, and similarly holes can appear with different masses. So the fundamental properties can depend on the band structure. Electron and hole are not same. A state which is a linear combination of electron and hole is same as the state that you get after conjugating it. So it's like E plus H conjugation. What do you get? H plus E. So E plus H and H plus E are same because addition is commutative. Sorry, right? So that is the idea that one is proposing here.
As the seminar comes to an end, I want to express my heartfelt gratitude to our principal, Dr. Ajay Sharma, for their invaluable support and leadership that led to the successful conduct of the seminar. Now I would like to invite him for the vote of thanks.
Dr. Sanjeev Kumar from ISER Mohali, my learned faculty members from the college and other colleges, and dear students. Well, I was thinking at 4, when I go up, there will be actually empty hall, but I don't know whether it's seriousness or the strictness of the teachers. But certainly the talk, I could attend only a few part of it, though I'm not having the background of physics now, but I could understand and comprehend few part of it. Because his way of communication and the simplicity with which he was explaining the position, that was highly encouraging.
And I hope most of the students who are having the undergraduate classes must be in a position to understand that. And those who are having the PG classes, they must be in a fully position. But what I was liking was that instead of going into the jargon of the mathematical calculations and the scientific details, he was making the things very easy for all of us. And that's something which is desired from a good teacher. Otherwise, in most of seminar, we find out that a person who is coming as a keynote speaker, as valedictory speaker, they used to have such a difficult languages and concepts that most of us fail to understand. But that was not his case, so I have a great appreciation. And you know, it was the third national seminar of Department of Physics, and every year they're organizing with the same zeal, and it has become a normal routine now. And I was thinking that we should ask other departments also to organize the series in the same fashion. I congratulate the organizers, particularly organizing secretary and HOD for the organizing this successfully. And because entire department is sitting, so entire department needs appreciation for that. So congratulations to all of you, and hopefully whatever we have learned today, we will be continuing the same in future also. As sir has told you earlier also, here he is just giving you the ideas of the concept and such areas, and now you can explore in future. Sometimes after 2 years, 3 years also, you just come to a phase when you decide to write a paper, or you are at a phase when you start doing your own research. Such seminars just remind you this is an area where others can work and we can progress in that direction. So I'm thankful to all of you for sparing the time, and especially to our key speaker, those who have come in the morning in the inaugural session, the technical sessions, and thanks a lot. Thank you.